Just slideshow mode.
Okay, slideshow.
Perfect.
Yeah, this is perfect now.
Okay. Does presenter view work actually? You know? Hello,
Joe. Yeah, it works.
Do you know if presenter view works or not?
You mean the cursor, or yeah?
No. I have a choice of slideshow or presenter view on PowerPoint.
No,
I'm just wondering if presenter view works.
I assume it's perfect now, Joe. It's good.
Okay, I will not fiddle with it in that case. Okay, fair enough.
Looks good. So yeah, I think we can start in 5 minutes, but let's not touch anything. So how have you been, Joe? Good to see you after a long time.
Yeah, well, confining like everybody else. It's all a bit crazy. Where are you actually?
Now I'm at home in Daejeon, in Korea. So which is pretty. It's 10 o'clock in the evening. Yeah. Okay.
Wow.
And where are you now?
I'm in France, actually. Yeah.
Okay. Yeah.
Not in Paris, outside.
I see.
Yeah. Yeah. Trying to, keep as few contacts as possible at the moment. It's a complicated moment. Yeah.
Yeah. How is the vaccine situation? I mean, are you in line to get it, or you already got it?
Well, I'm old enough, so I got it, and I had my second dose in a day or two. But there is a limit. I think younger people, people 70 or below are not getting it yet. So it's all a bit crazy.
Yeah, it's better to be more cautious. Yeah.
Yeah. They just don't have enough. How about where you are? How is the situation?
So in Korea, the vaccination has not been started, even for the elderly or the medics. But the point is that here they could have had a very good control. So the total number of deaths so far is still less than the flu. So it is like a 1,000 few. And then, so there are few hundreds of the contraction every day. But yeah, these are usually... they somehow, the economy is running at the same time. They control that it doesn't spread to more than some number of people per day. So it looks like that they don't find the necessity to go for the vaccination at this stage. But I expect that by end of summer, they are going to have a mass vaccination for everyone before the next winter. But by then, I think they're just waiting to see which one to go for, the AstraZeneca or Pfizer or, whatever. So they are waiting practically for the other countries to see the result.
Okay, that's cautious.
So Nima, do you have any announcements before the session?
The only thing is that because today we start our contributed talks and then we have parallel sessions, please have a look at the first page of the conference. Then you can find two links. One is the main room, which is here, and the presentation with an index A will be presented here. But you can find the program there. So there are some presentation with index B, which will be on the second, on the room number 2.
So Nima, why not just, when we start sharp in 2 minutes, you just have a brief explanation to people, and then we'll start.
Okay, it's great. Yeah.
Because I think some people will come just on time. And
yes, sure, yes.
Okay, shall we start? Okay, so good evening, everyone. Good morning, good afternoon. It depends on where you are. We are going to start the third day of this interesting meeting. So far, we had 2 very successful days, lots of very interesting talks and lots of exciting discussions. So before we start with Joe for his presentation, I think Nima would like to give some information about the contributing talks, which I asked him to talk first, and then I will get back.
Okay. Hello again, everybody. Welcome to the meeting. Today we start these contributed talks, so we have parallel sessions. For the information, please go to the first page of the website, our website, and then you can find 2 links. One is the main room, which is here, and the contributed talks with index A will be presented here. The other ones with index B will be on the room number 2. I will let you know more details in the break. Okay. Thank you, Arman.
Okay, thanks, Nima. So, okay, we are going to start, and please tell your colleagues that all these talks would be broadcasted live on YouTube. Again, the link is on the first page of the meeting. So, all right, so we have the first presenter of today is Professor Joseph Silk from EOPED, John Hopkins, and BIPAC in Oxford. So he's going to talk about Are Dwarf Galaxies a Challenge to LCDM? Very interesting topic for a long time, and then we will see what is going on. Joe, please go ahead.
So, greetings, everybody. Hello, all. It's a pleasure to be here virtually, at least. And I'm going to take you to one of the crossroads in cosmology, one that you haven't heard much about yet, but one that is an interesting topic as a challenge to our standard lambda CDM model. So on this opening slide, you see images of the ultra diffuse dwarf galaxies, some of them just amazing objects. And I'll be discussing their dark matter properties and how much of a challenge they are to our modeling of lambda CDM. So let's begin with a little review of the structure formation story in a fairly general way. So the blue line shows you the observations of the galaxy luminosity function. And the red line shows you the theoretical prediction of the galaxy mass function, basically the pressure theory. Now, obviously the observational data is fixed, but the theory you can slide up and down because the normalization is somewhat uncertain, maybe very uncertain, and you sort of can force it to match at one point. This is the famous L star, the characteristic luminosity, if you will, of the Schechter function, luminosity function. And then you can read off a mass, because the theory is in mass units. And lo and behold, you get roughly the right mass. So that already is an amazing, interesting success story in a very general way, that you get the mass-to-light ratio more or less okay. But there are real problems on small and large scales. You can see there's a huge divergence for small galaxies and one for large galaxies between theory and data. So we resolve these issues with feedback, let's say with input from, in one case, exploding stars, in the other case, supermassive black holes, that basically suppresses star formation and reduces the red line to the blue line. And you can see our aim is to explain galaxies. You see a couple of examples of a disk and a spheroidal galaxy on the right. The spheroidal has a big black hole in the middle. And it's now very quiescent, but once it was not. And maybe this was the underlying explanation. So we've now performed wonderful simulations, my colleagues have, of large-scale structure and galaxy formation. And you see over here on the right, examples from the FIRE suite of simulations, hydrodynamics, feedback, gravity, etc., all thrown in. And on below that, from illustrious TNG50, this time of a massive sombrero-like galaxy. And the amazing thing is that the pictures are, maybe as good as the real thing, maybe even better. We can't really tell the difference. Well, I'm not sure what this actually tells you about our understanding of fundamental physics, because there are many, many knobs you have to adjust in these simulations. But nevertheless, it is quite a success, really, to see that we have no problem with adding baryonic physics to account for the morphologies, the properties, the rotations, the spins of galaxies. On the bottom right, you see the story for very large scales. And here you compare the cold dark matter predictions in blue, normalized and selected to be consistent with a similar approach taken to the simulations, where you now have many, many mass points. You assign light to a mass point. You obey all the usual rules for large-scale structure formation, instability, etc. And lo and behold, you find your simulated universe looks very much like the observed universe, basically telling us that the cold dark matter ansatz, one of the major underlying assumptions here, must be more or less correct. So that's all very nice, but there is a problem. Let me tell you now about the dirty side of the story. On the bottom left, you see a classical simulation of the dark matter substructures around the Milky Way-like galaxy. There are many, many of them. And in the middle, you see a survey of all the dwarfs around us in the Milky Way. And there clearly is a slight mismatch in the numbers by orders of magnitude. So what on earth is going on? We have to wonder about this and address this. So let me take you through the issues that we try to resolve in reconciling dwarfs with the standard model. And it's not just the numbers, as you'll see. There are a number of other aspects of the dwarfs that are a challenge unless you model them carefully, as I will try to argue for you. So here are the topics that I'm going to cover then. I'll talk about the numbers of dwarfs, their diversity, and the question of how we reconcile the predicted cusps in the dark matter with what are often observed as cores. I'll talk about the radial distribution in galaxies, which is an interesting question. I'll talk about the vast planes of satellites of dwarfs around massive galaxies. Then I'll move on to feedback from intermediate mass black holes. I'll talk about what we call the too big to fail problem, why it is that a lot of these dwarfs have not lit up. They should be big enough to make stars, etc. And finally, I will then address the role of exotic dark matter, which is often introduced as a solution of many of the dwarf galaxy problems. I'll try to give you my views on that, whether that's a good direction to go in. So let's begin with the numbers. Okay, so top right, you see simple prediction of the cold dark matter model versus data in reddish orange, and there's a huge discrepancy on the smaller scales, as you saw before. But one way to address this is to bring in warm dark matter, which traditionally having a neutrino mass of a few keV suppresses small scale structure. Compared to the cold dark matter model, that's a solution we'll see later that maybe is not particularly successful so far, but it's an illustration of what one can try to do for a more exotic explanation. But in fact, the whole problem has probably gone away now that our modelers of dwarf galaxies in the vicinity of galaxies have put in the right physics. So one has to worry now. You take the observations and you allow for the galaxies with their orbits to suffer the physics of dynamical friction, the physics of tidal disruption, and stripping by the ambient gas, all of this. So all these effects go in. And lo and behold, it's the small satellites, the most easily perturbed and become sufficiently diffuse you can't see them in the current round of surveys. Maybe there are traces there if we look very, very carefully, but we have yet to find evidence of missing satellites. And this then suggests then that whether you go to cold dark matter or introduce variants of warm dark matter where you put in physics to suppress small scale structure, you're not seeing a huge impact on the observations, which can be more or less explained by any of these models once you allow for the observational and baryon physics issues of the environment. So that seems one issue that maybe we should be worrying about much less, the numbers game. Now, the second issue is what's been called the diversity problem. So again, top right, when one does numerical simulations, you find that, and here we're looking at the circular velocity, which is a measure of the dark matter content within a certain radius. You see, the models give you, the orange line, the simplest models, but the observations are all over the place. They have a wide range of dark matter content. So what is going on? Something is clearly missing from the modeling of the galaxies, perhaps. Well, again, it seems to be a question of putting in the right baryonic physics. And so here you see an attempt to do just this in the fire simulations, where you add the effects of feedback and you allow the exploding stars, which interact with the baryonic gas, to shake up the potential in periodic episodes of star formation and star death. And this has the effect of essentially by dynamically heating up the dark matter. And so you can see one can recover compared to the observational modeling, which itself is uncertain in the colored areas. One can recover the widespread one sees for many of the dwarfs. And so this has been pursued now for the smaller dwarfs as well, with the highest resolution simulations to date. And here, for example, compared to the observations, which are the X's, you can see models from this high resolution simulation, which show again for rather low mass objects, you also get quite a diversity of dark matter contents, more or less, as we see. So again, this seems to be a problem that has come and maybe gone away, the diversity problem. Let me turn next to what has been called the core cusp problem. So here we have the issue that when you measure rotation curves close in and infer the density profile, that's the parameter plotted vertically, you infer typically a very soft profile, a core. That's the alpha near zero there. In fact, the simple theory, NFW theory, predicts typical cusps as 1 over R. So again, how do we understand this? Well, again, it's a question of inputting more complicated baryonic physics. Typically, this is done by using supernova to shake up the potential. But there's another issue, which is probably even more important, that's been largely neglected, and that is you have to allow for the non-sphericity of the orbits of the stars you're using for measurements. And clearly, if you have a radial orbit and you measure velocity, you're underestimating or you're getting the mass wrong for a real three-dimensional orbit. And so this basically is a way of, when you apply these corrections to the data, of essentially turning what you think might have been cusps into cores. You're basically over-interpreting the amount of dark matter by assuming an isotropic profile. Okay, so that's another interesting wrinkle on this. And I would say the combination of the physics effects of stirring things up by supernovae, I'll come to other ways in a moment also, and more realistic modeling of orbits does shed a lot of doubt on whether there really is a core cusp problem. So moving on, here's another solution which involves black holes. Now, it's an interesting thing, I just want to point this out, that one way to change cusps into cores is by heating the galaxy. In fact, basically, this was used, in fact, at one point to rule out too many black holes altogether, because you would destroy the low surface brightness galaxies. But in fact, if you adjust things right, and this means having a few % of dark matter in primordial black holes, you can in fact turn cusps into cores, and this shows you the time sequence that does that. So you either weaken considerably or even destroy the cusp after roughly a few gigayears. And so that's another dynamical solution to the core cusp problem, as well as the more complex baryonic feedback and orbit modeling possibilities. So we have many, many ways to go in addressing this problem. And that is one of the intriguing things about all of this. We have to figure out which is the better solution, perhaps. We're far from that yet. But it does tell us there are many, many routes to explore before we come to any conclusions about there being some severe anomaly in the data. So here's another issue that's been raised repeatedly in the past. When you look at the Milky Way satellites and you compare the predicted results for the radial distribution from a pure dark matter model, you find that the dark matter satellites have this strong radial increase towards the center, but the observations simply do not. There's a deficit in the inner galaxy. And now this is simply due to a combination of dynamical friction, tidal disruption, the effects of the Milky Way disk, basically. And so again, when this is included in the modeling, you get a perfect match. So the radial profiles of satellites seem no longer to be an issue worthy of considering it as a challenge to our standard model. So here's one more topic that has been worried about a lot in the past by a number of my colleagues. You heard a talk yesterday by Pavel. This is the vast plane of satellites. So these are impressive structures. So the Milky Way has many of its satellites seem to be in a giant thin plane. Similar comments seem to be true for Andromeda and Centaurus A. So the question is, what on earth is going on? This seems to be very hard to concoct in the standard picture of the cold dark matter theory. But as the data gets better, we are being pointed to a possible solution. So this has come from the Gaia data in particular, where by tracing the orbits of the satellites, we've realized, colleagues have realized, that there is this vast plane divides up, and some of the satellites around us, for example, are in a plane around the Large Magellanic Cloud. And so this means it's a combination of satellites guiding dwarfs and our own Milky Way halo, and the interface between the two makes the interpretation much more complicated. So when we move on to a recent attempt to dynamically model all of this, I show you the results claim the probability of finding a thin giant plane without the Large Magellanic Cloud. It's 2%. But once you add in the LMC to your modeling and do a suite of simulations, you find that it's up to 16%, which is nothing really significant to worry about. So of course, these are not, maybe this is not the complete solution, but it tells us that we have to be very, very wary about regarding satellite planes as a challenge to the standard model. Doing the dynamical modeling properly with our major satellites is key to doing this, to doing a better job of statistical inferences. So the final problem, the classical problem that I want to address, has been called the too big to fail problem. And so you see this summarized in the lower left, where from the simulations, the red lines give you a number of different rotation curves, and the black dots give you the positions versus radius of the classical Milky Way satellites. And you can see where on Earth are the bigger satellites in the bigger galaxies, because you see many of these galaxies have higher circular velocities than where we see these satellites, which means they should have enough mass to retain their gas against supernova-driven output and dissipation. That's the classical explanation of why the smallest dwarfs are stripped. In the early days, they were gas-rich. 1 or 2 supernovae was all it took to drive the gas out and reduce the efficiency of star formation. But go to a big dwarf, it's much, much harder. And the consensus is that supernovae cannot do the job. Well, again, do you at this point wave your hand and say, I give up, lambda CDM has a problem here, or is there something you're missing? So the new development that we're missing, and have just begun to realize this in a number of recent papers in the past year or two, is that it's black holes that resolve this problem and their feedback. So we know that black holes power much of the activity we see in quasars, the vigorous outflows we see. In giant elliptical galaxies, it's the early phases of accretion onto the black hole and the outflows that are responsible for quenching star formation and limiting the giant ellipticals to the luminosities they have. Well, now it turns out that when you go down to dwarf galaxies, and on the left, and I plot what's plotted here is the kinetic energy output versus the AGN luminosity, you find that dwarfs have incredibly active black holes too. Obviously, they're scaled down in size, and many of these were discovered recently thanks to radio observations of dwarfs. The conclusion seems to be, and these are just the ones we detect in the active phases, of course, but it seems to be that there is a strong output that can essentially quench star formation in the dwarfs per unit mass as in the big galaxies, and maybe it's even more efficient because we're dealing with much, much lower potential wells. So that's a fascinating part of the story too. And of course it goes on. Here you see star formation rates now from simulations compared to different types of black holes. And as you make the black hole fat, obese, that is, we measure black hole masses from simple scaling relations, but there's a wide scatter, so some fraction of them are fat, others are thin, but it's the ones with the fatter black holes that have more output, and they quench the star formation very effectively. So again, this tells us that quenching is very important, maybe not for all dwarfs, but if their black holes are shown observationally to be slightly overmassive, that might go in the right direction. And that is somewhat of a controversial issue at the moment, just what the scatter is in black holes in the dwarfs, because the data is sparse. And indeed, regardless of obesity or not, it turns out that recent simulations find remarkable outflows in dwarf galaxies. Again, the low gravitational potential makes a huge difference. And so radiation pressure or kinetic energy-induced, wind-induced outflows are common from black holes. And so these are simulations of the velocity field seen edge on in a sample of similarly dwarf galaxies, and it's significant. And again, all of this, I think, plays a hugely important role in understanding the too big to fail problem. We have to include all of this physics before we can come to any simple solution of the problem. Okay, or resolution. And it gets even more fascinating because here you see a recent study with Muse of a giant cluster of galaxies, and it's with huge radio lobes, X-ray emission, etc. And what was studied here was the fact that towards the outskirts of the outflow, there are a number of small dwarf galaxies, and they were all very young. And so this is, an interesting coincidence maybe, but could it be telling us, which seems more likely, that there's been some feedback effect between the black hole outflow and the properties of the dwarf galaxy? If these were gas rich, and they would have been at these redshifts, which are indicated there, then they would have been compressed, overwhelmed by the radio plasma that swarmed around the galaxy in this vigorous radio source and X-ray source, and that would compress the gas and lead to star formation. So it may be that star formation is really modified by AGN activity, which makes it even harder to come to simple conclusions about the role of dwarfs as probes of our cold dark matter model. One has to include all of this physics in their formation, their environment, etc., before drawing any strong conclusions. Okay, so it gets even more fascinating. So here is a recent study of, from, in this case, the Dragonfly telescope, of ultra diffuse dwarf galaxies. Now, they have found a number of them. I showed you an example on my opening slide. But in this particular case, a couple were discovered that seemed to be highly deficient in dark matter. So what on earth is going on? Normally, dwarfs have a lot of dark matter. They have a lot of variation too. I showed you that in an earlier slide. But these two cases, and possibly one or two others, indicate deficiencies. So what is going on? Well, at the center of this group, there is a significant AGN outflow, an active galaxy. And it may be that, again, the impact of this has played some role in the physics. Here's another possible example, though, that may be slightly more pertinent. The bullet cluster has this amazing separation of dark matter seen by lensing and the X-rays, and so it's as though we have a ship passing in the night. The gas simply decoupled from the dark matter, was shocked in the collision, etc., and the dark matter just passed on through to give you this more broad distribution. So it could be that collisions would lead to similar separations for dwarf galaxies. They could have collided with other galaxies, and that would lead you then to looking for interesting aspects. Somewhere nearby should be a lensed image of a darker system, and maybe if there are AGNs, they should be not necessarily be in the centers of these systems. They should they would have suffered some dynamical history that's complicated. Okay, so let's go to the simulations. So a large box of simulations from the Horizon Consortium. And when they look at a large box of dwarf galaxies, they find, again, some small fraction of dwarf galaxies seem to be quite deficient in dark matter. And these are the ones that have gone fairly close. They're not the ones on large pericenter orbits. Are the ones that have been more restricted near the center of their host galaxy, and they may well have been stripped of in their passage, separating dark matter, perhaps by tidal effects, etc., from the gas, which suffers, responds differently. Okay. So this is sort of interesting too, that simulations are showing a class of dark matter deficient galaxies. And here's the control sample on the right. The typical ones have the standard whatever frequency and standard amounts of dark matter. This is a minority of galaxies that might have unusual orbits, suffered some history that led to them undergoing differential stripping that diminished their apparent dark matter content. So one more puzzle about ultra-diffuse galaxies. Here's one recent example where you can see an amazing number of globular clusters. I thought I would show you this as an indication that we know really very little about these dwarf galaxies. How on earth could they, what went on? Might it have been, collisions that led to, clouds being forcibly contracted, collapsing, making globular clusters? That's one of the options, but I'm sure there are many others. This might just be the relic of a bigger galaxy, a puffed up relic of something much bigger that naturally would have had a large number of globular clusters. Maybe that's not a big situation, but it does mean we have to be incredibly careful when we model our dwarf galaxies and use them basically as templates for testing cosmology. So here is another recent prediction and discovery too. So it turns out that in the course of making a galaxy, there are many substructures in the standard model and they interact with each other. And so at the end of the day, there's a lot of buffeting around dynamically. And the central black hole in a dwarf galaxy, I mentioned how they've been recently found, need not really be at the center. It can be off-center because of this dynamical effect. And this shows you what happens with a couple of substructures of dark matter as they form or merge in a galaxy. And you get, kiloparsec, tens of kiloparsec offsets. So this is wonderful. It's also been seen directly in other simulations. Here's another recent example of a merger of two dwarf galaxies, small one with a bigger one, leading to an offset of an intermediate mass black hole. And then you may wonder, what on earth do the observations say? Well, it's amazing. So here's a subset of a recent study using precise radio data to pinpoint the AGN. And you can see in many cases it's off-center, okay, from the dwarf galaxy. So there's some interesting physics here, and it does seem to be a measure of the complexity of the formation process involving, I would say, the standard gravity that we know and love. Okay, so this brings me to the question of exotic dark matter. So we have so many varieties now of dark matter. Most of these are justified. Of course, there's some beauty in the intrinsic physics. I'll be the last to deny that in some of these models. But a lot of it is justified by the fact that colleagues say, aha, dwarf galaxies have a problem. They have cores, they should have cusp, etc., etc. Let's invent some dark matter that can account for this, self-interacting dark matter that fuzzes things out naturally, warm dark matter. And there are many, many varieties of dark matter you can bring in to basically satisfy any problem that you think is a problem in the role of dwarf galaxies in the standard model. So let me just give you my 2 cents on this. Einstein had a really strong motivation when he invented general relativity. He said that, Mercury's perihelion advance had been observed for hundreds of years, and it was a significant discrepancy. And he explained that with a new theory. The anomalies in dwarf galaxies, maybe they do provide hints of new physics. They certainly cannot be explained in dark matter-only simulations, that's for sure. But the trouble is, I don't think they meet the threshold for a new paradigm. When you add the baryonic physics, some of the anomalies have disappeared. Others, well, we're just beginning to get to grips with the complexity of the baryonic physics. I would not bet on anything that you think is an anomaly remaining that way for very long, at least until we have a much more thorough understanding of baryonic physics. So let me begin to wrap up. I would say that the the popular exotic dark matters are actually in difficulty. There have now been a collection of new satellites discovered in the Milky Way, and it turns out that the most popular variants of exotic dark matter, and that's warm dark matter, fuzzy dark matter, and self-interacting dark matter, to name three. I don't have time to go into any details, but all of them are running into strong constraints now from the observations. For example, in the self-interacting hypothesis, you can't somewhat explain the wide range of dwarfs you see with cores of self-interacting dark matter, and so on and so on. Okay, similar comments of fuzzy dark matter, and with warm dark matter, we're running into strong constraints from the Lyman alpha forest, etc., etc. None of this is maybe ironclad, but the consensus from the galaxies is that they are in difficulty, I would say. So that, I think, is where we have it for the more exotic dark matter variations. So a few words on intermediate mass black holes. Are there indeed, I think they play a really important and unexplored role in our modeling of dwarf galaxies. Many may have them. In many cases, they haven't, they were active a long time ago. We only see a remnant of them now.
Just sorry to interrupt you, but maybe you better wrap up your talk so we have a few minutes for the question and answer too. Thank you.
Indeed, I'm almost there. Thanks. The anomalies that we see are due to some combination, I've argued, of supernova feedback and intermediate mass black hole feedback. And they're not anomalies. It's a signature of interesting new physics. I don't think there's a compelling need to bring in new physics or new gravity to handle dwarf galaxies. I would say there's now evidence of the role of intermediate mass black holes in dwarf galaxies. From the outflow kinematics, the observed occupation fraction, hinting to something much more dramatic in the past, the quenching, the feedback, and the feedback drives sporadic bulk gas motions in the early phases, just like supernova do. All of this has, and then finally we have the offsets of the black holes. Again, a prediction of this complex modeling. And so my final line, the bottom line is, all of this is great. I think it's promising. From the dwarf galaxy point of view, we simply need much, much better simulations. And of course, at the same time, better and better data to really understand the dwarf galaxy problem and decide if it really has any potential for challenging lambda CDM. Thank you.
Thank you so much, Joe, for a very interesting talk. So we have about 7-8 minutes for some questions. So if you have a question, please raise your hand so we can see you are coming. So okay, Mike has a question. Mike, go ahead.
Oh, it's Mike Hudson. I had a question about the thing that you flashed over very briefly about the potential AGN radio lobe triggered star formation. So in that scenario, I'm trying to, I guess we can't tell directly from the observations, but I'm trying to understand whether, if that is actually what's going on, would this be triggering just in the in the gas itself, or would it be triggering star formation in, dark matter halos that are orbiting within the group or cluster?
So, what I'm going to tell you is just could you sort of terminate the presentation, please, so I can see myself. It's gas. Basically gas clouds that will be affected by the hot, radioplasma, expanding radioplasma with extremely hot plasma, high pressure. It'll overpressurize gas clouds. It'll overpressurize gas-rich dwarfs too, but it will not affect the dark matter directly. So that's sort of the answer. It will turn gas clouds, induce bursts of star formation maybe, and give you a youngish signature. Of course, maybe there are other explanations too. It does seem a bit of a coincidence with finding, these cases of anomalously young things, young starbursts perhaps, small starbursts in dwarfs at the edge where of the expanding alpha, where there's just been time to catch these things in their full brilliance. They would have faded had it happened much earlier, perhaps.
Okay, I'm not sure that Mike has still the mic or not, but anyway, we have 3 other questions. So Mike, if you have a question, maybe in the break time, we can continue with Joe. So Marcel?
Hi, so I'm Marcel Borowski. Wanted to thank you for mentioning planes of satellite galaxies. I think that's often glossed over, especially when there's no solution to be presented. Now you presented a possible solution. I was a bit confused by that. You showed this plot from Patel et al. To motivate that LMC infall could kind of result in these planar flattened distributions. I was a co-author on that paper, and we explicitly find that none of the observed classical dwarf models of the Milky Way have been brought in with this LMC system. So in that sense, this solution might work in a general simulation sense, but for our current specific situation, it doesn't seem to apply. So my question would also be, how does this help address these structures outside of the Milky Way? So we have one in Andromeda and one in Centaurus A, and we don't see any major satellite galaxies influencing the satellite distribution there.
Yes. So could you terminate the display, please, so I can see myself? Thanks. Yeah. So I think all I was trying to argue was that having a satellite, and there is Gaia evidence of a plane around the LMC, for example, etc., some of these other satellites, is reducing the significance, and that's what I found, statistically speaking, in the results. That was what was found in the results I showed from the Simon et al. Paper. So I think it's if you point to a specific example, you can always say, there are just big fluctuations. I think what we care about is the prediction statistically from the simulations as to whether there is, a problem. You can't just point to one object and say, aha, we live in some bizarre situation. I don't think that makes much sense. You mentioned 2 others. The numbers are very small. The data maybe is perhaps not as strong as you look further away. And so I just simply think the statistical inferences are weaker than have been claimed. I'm not saying that the problem has gone away completely, but the dark matter simulations have an awful lot of freedom in still when you adjust various parameters. So I think I'm not sure I don't think we're at the end of the argument by any means.
Okay, Joe, I was told that you should terminate the full screen mode yourself. But anyway, we are just seeing your presentation and yourself, so for us it is okay. So, okay. Sean, you want to talk?
Yes, okay.
Your hand is up.
Yes, okay. So thank you very much for a nice talk. I want to know your idea about the high redshift quasars and the supermassive black holes. Are they consistent with this cold dark matter paradigm or not?
Yeah, so I think possibly what you're referring to is the fact that it's hard to understand the high masses that we see for supermassive black holes at very high redshift. Do we need some sort of anomalous seeds?
Exactly.
Grow them early, okay. I think there's just, again, so much astrophysical freedom. We have, direct collapse options that have not been properly explored for generating million solar mass seeds. We have super Eddington growth options, again, which can occur briefly, but in repeated phases. That might be another way to solve this. There might be big uncertainties in the initial power spectrum on smaller scales, which boost structure on smaller scales, enhance the number of seeds. So that's maybe a slightly more exotic direction to go in. But I think the astrophysics simply is still being explored. So I'm not convinced that it's a problem yet.
Thank you.
I guess your microphone is off.
Okay, sorry. So I think we can have very quick question from Oliver.
Does it work now?
Yes, we can hear you. Go ahead.
Okay, perfect. So thank you very much. My question is, you showed the different solutions for too big to fail and missing satellite, cast core. And my question is, if a particular solution solves one problem but doesn't solve the other problem, can we really say it solves the problem of the dwarf galaxies? Because as far as I know, no solution solves all the issues simultaneously.
So I think you've hit the nail on the head there. For example, it's one thing to invent a type of dark matter that can solve the core cusp problem, but there are always other problems too that it doesn't solve. And so that demonstrates to me there's a huge weakness. The beauty of baryonic feedback is that it goes in so many directions, from supernova explosions to AGN feedback, etc., and makes the situation so complex. You know, it's a bit like predicting the weather. We simply can't do that on very long timescales. It's very, very inaccurate. I'm afraid galaxy formation may be a bit like meteorology. There's no new physics in meteorology. Why should there be in galaxy formation?
Okay, Joe, thank you. We have one more question from Indranil. So please go ahead.
So can you hear me?
Yes, we can hear you. Go ahead.
Yeah, I just want to point out that the work you mentioned by Jenna Samuel on the satellite planes has not been accepted yet. So it's a bit dangerous using that to argue it solves the satellite planes. The other thing I wanted to mention is that so massive satellites are already included in cosmological simulations, such as Illustris, right? And we know that that in such simulations, satellite planes similar to the satellite plane around the Milky Way or Andromeda or Centaurus A are extremely rare. I didn't understand why just having the LMC there would solve the problem, especially as Marcel pointed out, there isn't something similar around Andromeda.
Well, I agree that satellite planes are rare, and that maybe makes them not so much of a serious issue for the basic model of lambda CDM. I think that this issue of whether there is an LMC type, a culprit to blame, again, I would just say statistically, if they're really rare enough, then they're not a problem. There are fluctuations. We just have to live with that.
So what do you mean by if they're rare enough, they're not a problem?
Example or two, and saying, gee, we're in a very special place in the universe. That's a very dangerous thing to do. So
that's right.
I think we need possibly to have more observations, more galaxies, more discussions of whether they have satellite planes. Having 2 or 3 examples is surely not enough to draw.
But sorry, all I would say to that is that these are the only 3 examples where we can observe the distribution of satellites in 3D in detail. And it would be quite unusual if in all 3 cases you have a thin satellite plane, even though it's quite rare in lambda CDM.
Yes, I agree. But the claim is that 1%, 2%, or 15%. And if it's 15%, then it is rare, but we don't worry about it so much. And that, I think, was the point of this paper that's still unpublished. Let's just wait and see whether their conclusion about satellite-induced enhancement of probability has any significant role.
Okay, thank you so much, Professor Silk, for a very interesting talk, and everyone who is attending. So maybe we should go ahead. Let's have a virtual thank to Joe. That's what we can do. So yeah, we can go to the next speaker. So Joe, you can stop your video and presentation. So thanks again.
Thank you.
You're welcome. So Eleonora, you should be around.
Hello? Yes.
Hello, yes.
Okay.
Okay, we have you. So I think now if you share your screen.
No, it says the session has a limit of 3 simultaneous videos, so I can't share my screen.
Okay, so Joe, we need you to stop your camera.
Okay. Okay, I will try to do that.
On the top of the screen.
Right.
Okay, so, all right. Okay, good. So Eleanor, can you share your screen now?
Yes. I think so.
And don't worry, we are 5 minutes behind the plan, but you will have 5 more minutes from the end, so.
Okay. Okay, can you see my screen?
Yes, please go for the full screen and.
Yes, let's see if I can. No.
It's perfect now. Okay, so next speaker is Eleonora Di Valentino. So she's going to talk about investigating cosmic discordances. So please go ahead, Eleonora.
Okay, can you see the slides moving?
Yes, we can see that, yeah.
Okay, perfect. Okay, so hello everybody. Thank you so much for inviting me here at this fantastic conference. Today I talk about investigating cosmic discordances, and I will review all of the tensions we saw in the last days. Okay, assuming my personal point of view. Okay, so the lambda dark matter model has been assumed as a standard model of cosmology because it can provide an amazing description of a wide range of astrophysical and astronomical data. However, this model is based on unknown quantities, and the physical evidence comes mainly from cosmology and astrophysics without a strong theoretical motivation. These unknown quantities are the necessity of an early stage of accelerated expansion, which produces the initial tiny density perturbations needed for such a formation that we call inflation. Then we need a clustering matter component to facilitate such a formation, and we call this dark matter, and then an energy component to explain the current stage of accelerated expansion, and this is the dark energy. But in the lambda dark matter model, we are choosing 3 really specific solutions for these quantities, mostly motivated by the computational simplicity. So for the inflation, we have a single minimally coupled zero-lonely scalar field. For the dark matter, a pressureless fluid made of cold and collisionless particles. For the dark energy, a cosmological constant term. So we have a 6-parameter model, and this seems more an approximation to a more realistic scenario, still to need fully understood. So in this context, the deviations from this model are expected, and the anomalies and tensions between the observations at early cosmological time and the measurements that we have at late cosmological time, if are not due to systematics in the experiments, can indicate a failure in the lambda matter model. So most of the anomalies and tensions we are talking about are involving the Planck data. The Planck data are a wonderful confirmation of a flat standard lambda matter cosmological model. However, these measurements are model dependent. This means that if we change the model assumed to analyze the data, we can obtain completely different constraints. And we have also the degeneracy, the correlations between the parameters, so that affect the observables in a similar way. So let's see the most statistically significant and persisting anomalies and tension. We saw all of them in the last days. We have the H0 value with the local measurement, A lens, that is an internal anomaly of Planck, S8 with the cosmic shear data, and the curvature of the universe different from 0. You can find an overview about these anomalies and tensions in the letters of interest we submitted in August last year for SNOMAS 2021. So the Hubble constant tension is so-called the tension between the Planck estimate under the assumption of a random matter model and the measurement by the Schuss collaboration R19, or the new measurement that just came out a couple of months ago. And okay, we heard a lot about this on Monday by Adam, but we have also many other measurements. We have other CMB experiments like SPT Pol or Hart combined with WMAP that is completely in agreement with a lower value for the Hubble constant. But we have also the baryon acoustic oscillation measurements, and we heard about this yesterday by Eva Maria, where we see that combining BAO and with the Big Bang nucleosynthesis data, we have H0 that is completely in agreement with the value obtained by Planck. Okay, this measurement is completely CMB independent, but still model dependent. Then we have many late time measurements that we can see summarized here. These are all in agreement with a larger value for H0, so there is no scatter around the value measured by the early time estimates. And we have, for example, the measurement based on the C-phase supernovae, the tip of the giant branch, and we heard about this a lot by Wendy on Monday. Then we have MIRAS, variable Giant stars, the measurement based on the water masses, on the full 2D Fisher relationship, the surface brightness fluctuations, supernovae second type, and the strong lensing. And if we take an average, okay, taking into account that obviously some of them are correlated, so this is an optimistic average, we have about 6 sigma tension between these late time measurements and Planck. Now, if we start to do a jackknife for the results, for example, we exclude one group of the data and we take the result with the largest error bar, that is that obtained excluding the C-phase, the measurements based on the C-phase, we see that we are still in 4.8 sigma tension with Planck. Now we can do the same, excluding 2 groups of measurements, and in this case, okay, we are excluding the C-phase and the strong lensing measurements because these are the most precise in this list, and we see that the average is still in 3 sigma tension with Planck. So we are considering different methods, calibrations and teams, and we see that even excluding the C-phase and the strong lensing, we have a 3 sigma tension. This means that to erase completely this tension, we need multiple and related systematic errors in the different experiments. So since these seem unlikely, we can try to change the model that we use to analyze the Planck data. So the most discussed extensions in the literature are an gene affecting number free to vary and the dark energy equation of state. Okay, for an gene affecting number is belongs to the category of the early time modification of the expansion history before recombination, and we can have a larger value for the gene affecting number, for example, with additional relativistic species after recombination or through self-interactions of neutrinos. And then we have the dark energy equation of state that is instead a late time modification of the expansion history. Okay, regarding the neutrino affecting number, this was used to solve the Hubble constant tension because of the really strong degeneracy that is present between N effective and H0. The point is that passing from the Planck 2018 release to the 2015, sorry, to the 2018 release, we are adding the polarization, and this way we are breaking the degeneracy for the early ISW. So we have now really strong constraint on genome affecting numbers. So a fourth neutrino that we need to solve the tension with H0 is ruled out at about 6 sigma. So even when we vary the neutrino effective number, we have H0 equal 66.4 plus minus 1.4 km per second per megaparsec, still in 3.8 sigma disagreement with Planck. Better is the dark energy equation of state. We are replacing the cosmological constant with the dark energy equation of state free to vary. So we have H0 in agreement with Planck within 2 sigma, but at the price of a phantom dark energy. Then we have many other specific extensions. Every day there is one proposal on the archive, and we summarize them here in the letter of interest of Thomas, but we will be having soon our review for all the new measurements and proposals in the next week. The point is that we are trying with these models to solve the tension that we see between Planck and R19, but in general there are also the other measurements. So, for example, if we take BAO, a combination of BAO and Pantheon, this is the green region here, we see that they are constraining the product of the sound horizon and the Hubble constant. So if we want to be in agreement with a larger value for H0, we need a lower value for the sound horizon. If we are instead in agreement with the Hubble constant measured by Planck, we need a larger value for the sound horizon. So if we want to have an overall agreement with all the data sets, we need something that can change the sound horizon and the Hubble constant at the same time. So a late time modification like a phantom dark energy can just change the Hubble constant without moving the sound horizon. So is in disagreement with the BAO data. While early time solutions, like for example the neutrino effective number, but also early dark energy, are moving along the right direction of the correlation, so they can lower H0, increasing the sound horizon. The problem is that CMB plus BAO plus Pantheon is still in disagreement at more than 3 sigma with the value measured by the Schuss collaboration. But let's look at another possibility. For example, an interaction between dark matter and dark energy that is not forbidden by any fundamental symmetry. In this case, we are modifying the conservation equations with this interaction rate that will be proportional to the dark energy density and the conformable rate via this dimensionless parameter quantifying the strength of the coupling. In this model, we have H0 that is naturally in agreement with R19 within 1 sigma, because we have a flux of energy from dark matter to dark energy, so just an upper limit for the cold dark matter. And this is a 95% confidence level. So since the CMB is measuring accurately this product here, matter density, and times the Hubble constant, the square of the Hubble constant from the position of the peaks in the damping tail. If we have less dark matter, we need a larger value for H0 to be in agreement with the data. So now we can combine them together, obtaining an evidence at more than 5 standard deviations for Planck plus R19, improving the chi-square for this combination of about 13. The problem is that if we simulate an experiment like Planck, assuming a fiducial model with a coupling exactly 0, and we assume and we analyze these Planck data, letting these parameters free to vary, we have a detection at more than 3 sigma for an interaction. So we have a 99% confidence level region range for Xi different from 0. And this is just due to the correlation between the parameters. So there is nothing in the fiducial model. This is just due to the correlation between the parameters that we have have in Planck. So we need something like BAO. These are simulated BAO. If we introduce BAO data, we can break the degeneracy and recover in just a lower limit for Xi in agreement with no coupling. So what happens if we do the same for the real data? When we add the BAO, we have just 1 sigma for Xi, negative Xi, and we have H naught that is larger again than the standard model, because in the standard model we have Planck plus BAO 67. Here we have 69.4. So the tension is now 2.4 sigma. We are still below 3 sigma. The point is that it's difficult to understand if this is an actual residual tension or statistical fluctuations, because the BAO data are extracted assuming a lambda Goddard-Matter model, as we saw yesterday, and the bias that we have for extended cosmologies has been tested for early dark energy models and late dark energy equation of state that can be parameterized by W0WA. So this kind of interacting models is difficult to understand if the BAO data may need to be revised in this context. So we have to be careful, in my opinion, when we discard the late time solutions, in general, one solution, because this is in disagreement with the BAO data. Okay, let's go to the second bullet point, that is A-lens. Okay, A-lens is the famous parameter that is rescaling the lensing potential in the temperature power spectrum. So the photons coming from recombination to us are deflected by the matter interposed, and this can be measured by the smoothing of the peaks in the damping tail. So we expect a lens equal 1, but we have a lens larger than 1 at 2.8 sigma, with an actual improvement of the chi-square on 9-10 points depending on the observable. And this is not supported by the Planck lens reconstruction power spectrum. Moreover, if we cut the temperature power spectrum into different multiple regions and we extract the parameters here and here, we see that they are in disagreement at more than 2 sigma. So it's true that the Planck data have an internal agreement, but between the different observables, temperature and polarization. If we cut the temperature power spectrum to multiple regions, instead these 2 regions are in disagreement, and we can solve the tension with this A-lens parameter fixed to 1.2. And this is true also for the new release, considering the polarization data. So this A-lens parameter is a consistency check that is failing in Planck, and is something we need to explain the internal tension of the temperature power spectrum. So we will go back to this, but now let's see what is the S8 cosmic shear tension. We saw this yesterday. This S8 parameter is defined as a combination of the clustering and the matter density, and is used to quantify the tension we see in the plane sigma 8 omega matter between Planck, that is the orange 2D contour plots here, and the cosmic shear measurements, CFHT lens, KIDS 450 at 2.6 sigma level, 2.5 if we consider Lyman alpha or DES, including the galaxy clustering, 3.2 KIDS Viking 450 combined with an array analysis of DES year 1. We have 3.4 sigma, as Marika showed yesterday, if we combine KIDS Viking 450 and BOSS. This is the blue region here, so this is really far away from Planck. And now with the new KIDS 1000 data alone, we are able, we reach a tension of 3.1 sigma with Planck. So again, this can be seen like an early late time tension, and again, all of the cosmic shear with lensing measurements are below Planck. There are many proposals for solving these tensions too, and a summary can be found in the letter of interest of Snowmass. But here I want just to point to this. Okay, if this is a lambda Goddard-Matter model, we see that we have this 2 sigma disagreement between Planck and the cosmic shear measurements. This is KIDS, and these are solid line 68, dashed line 95% confidence level. So if we consider extensions of the standard model, we can find something that can put them in agreement. The point is that if we vary lengths in Planck, we see that the S8 parameter is shifted completely in agreement with kids 450. So this length parameter is something that is a consistency check that is failing, is something that we need to solve an internal inconsistency of Planck, but is also responsible, in my opinion, for the tension that we see with the cosmic shear data. So let's try now to vary many parameters at the same time, because in this 6-parameter approach, most of the assumptions and simplification are no more fully justified. For example, we are assuming a total neutrino mass fixed to 0.06 eV, and this is a completely arbitrary value, the minimal value allowed by the laboratory experiment. We have a cosmological constant with the equation of state fixed to -1, that is not favored by any theoretical argument. We have the cosmological constant problem about the energy scale or the fine-tuning. We have in the standard model the running of the scalar spectral index fixed to 0, but if we are assuming a slow rolling inflation, we expect a running of the level to 10 to the -3 that can be measured by Planck. We are assuming the neutrino effective number equal 3.046, but we saw that it's really easy to change this number if we have dark matter. So why we have to fix this to the standard value? Finally, we want to vary length too, because we have two reasons. First of all, if we fix a length to 1, we can bias some of the quantities that are length related, for example, the neutrino mass. If in the standard model we are almost ruling out the inverted hierarchy, but if we let the lengths free to vary, the error bar are relaxed by a factor 2. The second point is that we want to understand if there is an extension of the standard model that can explain this anomaly in the Planck data. So we vary 11 parameters at the same time. The first thing that we can see is that the physics is not altered. We have just a factor 2 on the error bars, and there is no indication for new physics. So everything is in agreement with the standard model. The point is that here each knot is 73 with larger error bars, and this is due to the geometrical degeneracy that there is with the dark energy equation of state. And in the plane sigma 8 omega matter, if these are the constraints from Planck in a 6-parameter approach, these are an 11-parameter space, so they are not only relaxed, but also shift in the right direction to be in agreement with the cosmic banana. This is due again to the A-length parameter that in this extended model is the only parameter not to be in agreement with the standard value, and it has increased in significativity and in significance maybe, and this is now 3 sigma away from 1, and combining Planck plus BAO, we have that A-length equal 1 is ruled out at more than 99% confidence level. So there is no way to change this parameter here. If we now try to combine Planck with R19, we can see which is the best extension for the data for solving the tension. So here we have an early time modification and a late time modification at the same time, and we see that the preferred solution is again a dark energy equation of state. So this is the degeneracy that we have in the plane dark energy equation of state double constant for Planck. When we add R19, we rule out the cosmological constant at more than 2 standard deviations, and this is in disagreement with Pantheon and the BAO. If we look at the neutrino effective number, the constraints are really well they are really robust, so they don't change when we consider different datasets combination. And we see that there is this correlation between S8 and the A-length, so we can have a lower value for S8 if A-length is larger than 1. So now this is the point. In the Planck papers, we read that there is this anomaly in the range a multiple range that is between 1200 and 1500 in the temperature, and this can be fitted well by a lens, and there are many models that can fit these features that we see in the data. But between all the possibilities and all the models, assuming the general relativity is possible of the universe. So if we use Planck only data, we find a detection of a curvature at more than 3 sigma, 3.4 sigma, and this is fully confirmed by CASPEC, because this is the 99% confidence level region that we have. You can see that before Planck was there was a less evidence by Planck using CASPEC in November 2019 in this paper here, that was about 2 sigma. Now in the new version, this is above 3 sigma. So the two likelihoods of Planck agree very well, and they are finding a closed universe. So now we want to ask, is this due to the correlation between the parameters? Because we saw before for the interacting model, for example, that if we have a correlation, we can have a fake detection of something that is not there. So we simulate an experiment like Planck, exactly as before, assuming a flat universe, and we vary the curvature when we analyze this simulated Planck. And this is the blue line you see here, so we can recover omega k equals 0 with a precision of 2%. So, because we can break the geometrical degeneracy when we have CMB only data, because we have the gravitational lensing measurement in the power spectra that break the degeneracy. So the evidence we see is something that is indicated by the data, and with an improvement of the chi-square of 11 points with just 1 more degree of freedom, because we can cover the low CMB anisotropy quadrupole. So we are not only fitting better the smoothing in the damping tail, but we are also recovering better the lower quadrupole we see in the Planck data. And the same explanation was suggested by a study in this paper to explain the lower quadrupole that we can see in the WMAP data. Okay, now what about the other data sets? Okay, what about Planck plus BO? We saw yesterday, and we know, everybody knows that omega k is exactly 0 when you add Planck and BO, but you can do this combination in this when the curvature is fit to vary. Okay, if this is the agreement that we have between Planck and the BO data in a flat universe, so Planck is the green region here, and these are the BO data, you see that this agreement disappears completely when you let the curvature fit to vary. So we have a disagreement at more than 3 sigma, and if we look at the chi-square, we are using 8 data points correlated one with each other, so we can have 6 or 5 degrees of freedom, and the chi-square is worsening of 17. So we are in disagreement with the BO, and this result has been confirmed independently and analyzed independently by William Handley in his paper just published. And we are in disagreement with the full shape of the galaxy power spectrum. We will see more in the Sunny's talk. And we are in disagreement with the same lensing of Planck. Okay, this is the best fit that we have from the lambda dark matter model. This is the best fit from Planck when the curvature is fit to vary. That is really similar to the best fit we have varying A lens. This is because in a closed universe we have more dark matter, so more lensing. And in fact, there is this degeneracy between these two parameters. So if we fix omega k to 0, we assume a flat universe, we have this evidence for a lens larger than 1. But if we allow the omega k parameter fit to vary, we can have a lens 1 as expected in general relativity at the price of a closed universe. Now here we have to be careful. This is just a phenomenological parameter without a theoretical motivation. It's a consistency check that is failing in Planck, and is a useful parameter for many things. But on the other side, we have the curvature of the universe that is not a parameter beyond the standard model. It's just related to the energy budget of the universe. And this omega k, this closed universe, is able to solve the internal tension of the Planck data as well. So this was the disagreement at more than 2 sigma, and this is now the tension when we fix the universe to omega k to 0.045. So what about, again, non-CMB data? So we combine only non-CMB data. In this case, we are taking a combination of BAO supernovae and Big Bang nucleosynthesis. Okay, we see that in this case, we have still an evidence to 1 sigma, just 1 sigma for a closed universe, but with a larger value for H naught, that is 79.6. So completely in agreement with R19. And but the problem is that their disagreement comes from the fact that Planck, in a closed universe, is measuring H naught really low, about 54, increasing the disagreement with the R19 value, and in the plane sigma 8 omega matter doesn't behave like a lens and is increasing these tensions as well. So this is the reason why we call this a cosmic discordance. Now, what happens if we look at different CMB experiments? Okay, the ACT data release gives a fantastic result, a flat universe with good uncertainty. So we are really happy.
Try to wrap up soon. Time is over.
Yes. We're really happy about this result because this is a confirmation of our simulation. So with just a CMB experiment, we can recover omega k equals 0 perfectly. And the prior is not important, the low multiples are not important. But ACT is also measuring an energy affecting number, different from 3 at about 3 sigma, 2.8 sigma. And there is an inconsistency between Planck and ACT. We can see this here. They are far away one with each other, so they are inconsistent, and inconsistency using the suspiciousness statistics is 2.6 sigma level. Now, this is important because they are both of CMB experiment, both of them are assuming the same model, but they are in disagreement, so maybe is the model to be wrong. But let's see the last problem. What about Planck and Pentheon? They again are in agreement with omega k equals 0. But is this result robust? Let's vary more parameters together at the same time, replacing a lens with omega k now, and to test the robustness of this result. So we can see that Planck is ruling out the flat universe, is very well below the flat universe, is completely in agreement with Pantheon, F20, that is the Friedman measurement of H naught, R19, all of them are well below omega k equals 0. This is happening because all of them are ruling out the cosmological constant. So we have that Planck plus the luminosity distance measurements are excluding both the cosmological constant and the flat universe at more than 99% confidence level, or in other words, we have an evidence for a phantom closed universe at 99% confidence level. So now it's difficult to understand if this is really more or less theoretically convoluted than the lambda quadrant matter model, because we remove the fine tuning of the cosmological constant and we add the fine tuning of the curvature. This is just been accepted in a PJ letters. So this is my last slide. Most of the anomalies and tension that we see are involved in the Planck data, so it's really difficult to do a precision cosmology with this kind of problems. My advice is to watch out for the elephant in the room, because, okay, if there are systematics in Planck, we have to take them into account, and if this can be explained by a lens larger than 1, we have to marginalize over this parameter, most of the tensions goes away. But if there are no systematics, a lens is just a statistical fluctuation, as everybody is saying, then a lens is fixed to 1 in the standard model, and we have many tensions. So Planck results are not a confirmation of a flat lambda quadrant matter model. Okay, thank you so much.
Okay, thank you so much, Eleonora, for an interesting talk. I don't know who is in charge of statue. They could also, comment about the ACT or Planck. But anyway, I'm sure that there would be many other people to have questions. So if you have a question, please raise your hand so we can see you on the top. Okay, so Adam.
Hi, Eleonora. Very nice talk.
Hello. Thank you.
my question is very interesting. Much to unpack here. My question is, what do you think would be the most valuable future CMB observations that could help sort of split some of these degeneracies or probe some of these different possibilities in parameter space?
Yeah, okay. We hope to have CMBS4, but this is a ground-based experiment. The problem is that we need to remove the foregrounds, and so an experiment from the satellite allow you to do this, because otherwise you can have fake detection like the what we had, the scalar, the tensor to scalar ratio, no? at 7 sigma. So we need another satellite experiment, in my opinion, and there are proposals. There is PICO, there was a core, but has been, I think, is not been funded, and there is there are PRISM, I think. So another satellite experiment can allow us to understand better this problem. We hope that with CMBS4 we can do something, but we have always to use the Planck maps to remove the foregrounds from the data.
Thank you.
I just go follow the list. Shine question, but not too long.
Maybe. So, do you know of any model that can resolve Hubble tension?
Sorry, I can't hear you at all. Can you speak louder?
Oh.
Okay. Hello?
I think his connection is not very good. So we go to Marika first, and then maybe we can.
I just wanted to ask a little bit about the A lens and omega K. So you showed you vary A lens, you can alleviate the tension. But then when we vary omega K, the tension increases. Why is that?
Yeah, okay, this is what we call cosmic discordances. Because when you vary A lens, you have still that H naught is around 68, 69, something like that. When you vary omega K, you have a much lower value for H naught, so you are increasing the tension with S8 because they are strongly correlated.
Okay, so it's although the omega K and A lens are correlated with each other, when you translate the correlations to other parameters, it's not so straightforward then. Yeah.
No, this is okay. Yeah, you are increasing the discordances with everything. So.
All right. Thank you.
Okay, Pavel.
Can you hear me? Thanks for this very interesting talk. I think this work is really exciting. As you know, we emailed. And here's my question. Imagine that the universe were actually flat, but it's much more structured today. So structures for much more, right? So you have much higher contrast between underdense and overdense regions. Would that help in reducing the tensions with S8? Well, we know it solves the H0 tension already, so that point is gone. We remove the tension, and AL larger than 1 would be automatic because you simply have more lensing along the way, right? And omega K would, well, you'd have a flat universe anyway. So wouldn't that be basically a solution, like I explained basically yesterday?
Sorry, I didn't very much understood. Okay, so you are saying we have a flat universe, you have a lens larger than 1, but the lens is not a parameter.
Say again?
So the point is that a lens is not a parameter, it's not physically motivated. So if you believe that omega K in 0, you have a lens larger than 1, so why is that? Okay, there is no reason, there is no a physical motivation behind a lens. So at that point, in my opinion, the only possibility is that you have a systematics in the temperature power spectrum. You can't have a lens larger than 1.
It's
in general,
even I see.
Gravity.
I thought it's supposed to be a lensing parameter. Then maybe I misunderstood it.
Screen. still?
I can still see it, yes.
Yes, okay. If you, okay, here you are measuring the lensing coming just from the smoothing of the peaks in temperature and polarization, okay? While you have another observable that is the CMB lensing itself, that is the 4-point correlation function, the trispectrum. And this is giving a lens exactly one. So this A lens is not supported by the lensing coming from the CMB. You have just something strange in the temperature spectrum.
Okay, we'll have to think about it, because I thought if you have more structure along the way, you would automatically, you know, compared to a lambda CDM model.
Yeah, but you should have more lensing, I think, no?
Yes. Yeah, exactly. Yeah.
Yeah, but you don't see this more lensing in the CMB lens.
Well, that's what I'm saying. So you would basically solve all your problems if you allow for more lensing along the way, which is synonymous to saying that we live in a universe which might be spatially flat, but grows structures much more significantly, like I showed yesterday, right?
Yes, but I think in this case there is something strange in the CMB lensing itself, not in the A lens parameter from the temperature, but in the CMB lensing, the other observable that you can extract from the CMB.
Okay, thank you. Thanks.
So this here.
So I think Shine is back. So Shine, can you ask your question? Shine, can you hear us? All right, again, I cannot hear response from Shine. So Indranil, do you want, I mean, you should have a mic already, Shine. Maybe switch it off and then people will give you again. Because here I see that you have a mic. Well, I mean, I don't know, Nimad or Shant, can you say
Shaheen asked his question in the chat, so maybe you can read from there.
Okay. So, he's asking that, do you know any model that can resolve Hubble tension and is consistent with BAO and supernova data?
If I knew it, I think I had the solution to the cosmic problems. No, unfortunately, all the models that we have and that have been proposed, and there are many, all of them have some problems somewhere. So maybe they are in disagreement with BO, or they agree with BO, but they don't solve completely the tension with R19, or they increase the tension with the cosmic shear data and with lensing data. So at the moment, there is not a model that can solve everything at the same time. There are interesting models. There are really dark energy models, self-interacting stellar neutrino models, but okay, we have we don't have a solution, as far as I know, at least.
Okay, so we have one more question from Indranil. Quickly, just please.
Hello, can you hear me?
Yes, hi.
Okay, so I just wanted to ask, so we do have a proposal regarding the Hubble tension, which Moritz will be speaking about tomorrow. What I wanted to ask is, if I understand correctly, this and other types of data at very low redshift. So if you look at data only beyond redshift of about 0.2, 0.25, is that consistent with a Planck cosmology with a low H0 in the flat universe?
I think I'm not the right person to answer this question. Maybe Adam can say something.
Okay. Yeah. So, if you can still hear me, I mean, yeah, the H0 calibrations are all done more or less at low redshift. Below, I would say below 0.2. So, more or less, if you throw out everything below redshift 0.2.
Except the calibration, right? I mean, you still need the galactic-ified calibration, for example.
Yeah, I mean, you have to propose a specific scenario, I guess, and then I could talk about it. I mean, if you talk about, I don't know, something changing H of Z or something, you could do that until, you get to low redshift at redshift 0, and then you're going to smack into the fact that H of Z won't reach H naught.
Okay, so that's helpful.
I would have their specific scenario. I think I could just tell you, it's
okay,
it's,
but
distance ladders, are built from redshift 0. But we've also talked about you can go in the other direction with that and get up to the sound horizon and with a ladder, and then you'll have a conflict at the sound horizon.
Okay, no, there is a specific model which Martz will talk about later and is published. And another thing I wanted to mention briefly is yeah, you were mentioning the A lens was not a sort of physically motivated parameter. So I think what would happen in a non-cosmological scenario is that this would look roughly like boosting A lens above 1, but not exactly. I would imagine that there might be a scale dependence to it as well. So on smaller scales, there might be a slightly larger enhancement.
But this lens parameter has been introduced like this rescaling of this lensing potential. Okay.
Yeah, that what I was saying is this might be why there's a difference between like multiples below and above 1,000, possibly.
Well, the effect is usually at the high L, right? So
you are saying if we cut the lens into different regions, if we have a lens different from different regions. But I think we tried to do this once and we didn't find anything interesting. So I would say that is not a solution.
okay, thanks, Eleonora, for an interesting talk, and thanks. So I don't see any other hands raised. So I think now we have we have break. So maybe Nima or Shant, if you want, let's thank Eleonora first for the interesting talk virtually. Okay, so Nima, I leave the session with you if you have any announcement.
Thank you, Arman, Joe, and Eleonora. No, I just want to mention that in the next session, the second part of the next session, we have parallel sessions, and you can find the details on the web page. I mean, on the first page of the website. Okay, so enjoy the break. Have a coffee. Just Yacine, if you are around, please raise your hand. And you can see the second room, the room number 2 address is now pinned in the chat box. And guys, do you want to play the break music, please?
Hello, Yacine. I'm the chairman of your session.
Hi. Hi, Saurabh. Hi, Yacine. Let me
Hi.
just...
Okay, good.
Good. So you want to share your screen?
Yes.
Okay. So do you see the icons on top right?
Yes. The
middle one. I mean
okay. Oh, so it cannot be. Oh, okay.
No.
Application window.
There is one.
Okay. Okay, so if I share my screen, all right. I'm not sure. Does it do anything?
No, we don't see.
You know, I'm getting connected. So you say which browsers are best?
Chrome, maybe.
Chrome, okay, because I'm some other browser, so I'm going to reconnect with the other browser.
Okay, good.
Okay, thank you.
Hi, Saurabh. How are you doing?
Fine. I'm fine.
Great.
How's it going, Nima?
It's good.
Can you let me try this camera? Maybe I see you.
Yes.
Yes.
Yes. Yes.
How are you?
Yes. I'm fine.
Well,
maybe we should ask you to play something online.
Oh, thank you. Maybe. Yeah. So.
Because for the guys who are in the audience,
yeah, they are
is
Iranian music.
Saurabh is a professor in Sharif University, but he's playing music. Do you play setar? No.
Setar.
Yes.
Yeah.
So
make mostly setar now. Yeah. So that will start at 6
minutes. And Saurabh, you can do. I mean, we do everything for you, so you can just ask us to switch on a microphone or.
Okay.
Yeah.
Okay. Thank you. Yeah. Sure. So the talk is 30 minutes and 10 minutes, 15 minutes for questions.
Yes, and then because we have the other part, I mean, after that, after the Yacine's talk, we have this parallel session, so we should wait maybe for 2-3 minutes. People decide to be in each of the rooms. So. Okay, Yacine is here. So.
Okay.
Yacine, you have okay.
Yes, can you see me?
All yes.
Right.
Sure.
Okay. So let me share the screen.
Yes.
So if I choose my entire screen, does it do something?
That's really.
It seems like maybe I have to do something to.
Yes,
I have to.
You are on Mac. Kian, are you around?
I'm here. Sorry, I have to quit to allow my laptop. I'm very sorry. So.
Okay. It's good.
He's coming back?
Yes, I don't know what happened, but he had to move to his laptop or something.
Mm-hmm.
Okay, maybe this is going to work.
Okay.
The authorization to my laptop. Okay, good. And so now.
Yes.
Can you see my talk?
Yes. And start playing.
It's unclear. This is the entire window?
No, not yet.
What if I do full screen?
Yes, you do. Yeah, just play.
Yep.
Yes.
Exactly. Now
that works?
Perfect.
Okay, so I'm not seeing anyone, but I guess unless I can choose specifically the application. Oh, yes, I can do this. Good. So now that works. So,
but it's not full screen now.
Yeah, it's very small.
Yeah, but so, I'm gonna should be able to do it. Does it work like this now?
No. Before it was full screen.
Is it full screen now?
Okay.
Yes.
That's fine. Yes.
Okay, so I don't see you, but it's okay. So if there are questions, you're gonna have to tell me because.
Yes. Okay. Saurabh is the chairperson, so he will turn on his microphone to ask if there's a question or something.
Okay. Good. Are we supposed to be able to see the participants somewhere?
Sorry, I couldn't hear you.
Am I supposed to be able to see other people's videos somewhere, or I guess it's the first time?
There is only your video and mine. I will switch off my video when you start.
I see. Okay.
Yeah.
Got it. And if I guess there are questions in the chat, you will let me know.
Yeah.
I see.
And people raise their hands, and then we open their microphone.
Interesting. Okay. Yeah. So out of curiosity, because everyone is using Zoom, is this because Zoom you have to pay, I guess, as an institution, or?
Yes, we are using this platform. It's homemade in Iran, so we are using this for teaching and seminars and meetings.
I see. Yeah.
And a few months ago, I mean, I guess as far as I know, till few months ago, we couldn't use Zoom inside Iran.
Really? Okay, that's
yes.
Okay.
But then yes, for the conference, I heard that these days it's free even in Iran. I mean, not free. I mean, we can use that, but then we thought maybe it is a little bit risky to put conference.
Yeah, I see. And what's is there a reason? I mean, is Zoom particularly? I don't know.
Actually, because you should ask Zoom company.
Yeah. Oh, it's a decision from Zoom. Interesting.
Yes, it was from Zoom, not from inside Iran.
Interesting. Okay. All right.
Okay, now it's not full screen. If you, I think, when
okay,
you,
yeah. Okay, I'll start now. Right.
Okay, no, that's fine. Well, how's temperature there? Is it high?
Sorry, I also
you are using this cooler.
Can you see my screen again? Sorry, I keep messing up.
I lost your screen.
I'm sorry. I wanted to make something disappear, like little. Okay, now you see it.
Yes.
Yes.
Good. All right. I'm not going to touch anything anymore.
Okay, perfect.
Do you also see my video or just my screen?
Yes. Yeah. You see your video and your screen.
I see.
And
okay.
For the moment, we see actually Sohrab's video too.
Got it.
We'll have 2 minutes.
Okay, I'm going to give a timer too.
Okay, it's time to start. So let's start the second part of talks for today. Would like to thank Dr. Yacine Ali-Haïmoud from New York University. Is going to talk about the cosmology from CMB frequency spectrum. Please.
Okay, well, thank you very much for the invitation, first of all, and I hope one day I can come in person. I'm sure everyone is saying this, but yeah, I really hope I can come in person at some point. So let me start by recalling everyone of the CMB anisotropy big success story. Okay, so the success story starts in some sense in 1992 when the COBE satellite made the first full sky map of CMB temperature anisotropies. Following that, this really started, pushed CMB cosmology into the era of high precision. After COBE, WMAP followed, and then Planck, mapping the CMB temperature anisotropies with increasing angular resolution and sensitivity, and also mapping the CMB polarization maps. And from this, as you know very well, we have been able to extract cosmological parameters with a stupendous degree of precision. For example, this is how we know exactly how much dark matter there is in the universe within a % precision, even though we still don't know what dark matter is made of. So this is just a brief, ultra-fast recall of the success story of CMB anisotropies. Of course, the CMB has another aspect to it, which is the frequency spectrum. And the story of this starts in 1965 when Penzias and Wilson, the observational story at least, starts in 1965 when Penzias and Wilson detected the 3 Kelvin excess emission, which was then interpreted as the CMB by Dickey, Peebles, Roll, and Wilkinson. And from that 3 Kelvin number, it was already possible to have the first grasp, more accurate grasp of the thermal history of the universe. When was the universe radiation dominated, matter dominated? When did the universe recombine, etc., etc. It took 25 years to measure more than one number about the CMB free spectrum. And so again, the COBE satellite, and specifically the FIRAS instrument on board COBE in 1990, measured for the first time the full frequency spectrum of the sky averaged cosmic microwave background, and showed back then that the CMB had a perfect blackbody spectrum with distortions away from a blackbody below 1%. And note that this was simultaneously, I don't know if you can see my mouse. Hopefully you can see my mouse. This was simultaneously measured by Cobra, almost at the same time. They also measured the spectrum of the CMB.
We don't see your mouse.
You do not see my mouse?
No, I think you should activate it.
I don't know how I can do this. I'm sorry. Usually it works. But anyway, so the plot on the right. I'm gonna describe things and hopefully it will be clear. So the plot on the right. So the status as of 2021 of frequency spectrum observation. So while CMB anisotropies, there is a booming field after COBE DMR, and there are still lots of experiments planned to measure CMB anisotropies on smaller scales and deeper, etc. Well, the current status of CMB frequency spectrum observations is basically stuck to FIRAS. So FIRAS remains to date the best measurement, and measured the temperature. So after reanalyzing the data and combining with some other data, but the error bar is still determined mostly by FIRAS. The current best measurement of the CMB monopole temperature is 2.7255 Kelvin with an error bar of 0.5 millikelvin. And FIRAS, the latest limits on spectral distortions are basically that the CMB is a perfect blackbody spectrum up to no more than 1 part in 10 to the 4. And this is summarized by these two numbers, y and mu, which I will discuss in the next couple of slides, which we have upper limits from, again, from FIRAS. So there is a push from several members in the community at large to perhaps build the next generation of measurements of the CMB, instruments that could measure the CMB spectrum. And instrumentalists believe that it is indeed possible to measure the CMB spectrum to much better precision than what FIRAS did. And for example, in this white paper led by Jens Kluba, you can see all of the, whoops, I messed up again, sorry. I clicked on something. Do you see my screen? I'm sorry, I'll go back to it. I'm sorry, I clicked on something. Okay, everyone sees my screen?
No.
No?
No.
Okay, so I don't know what I did. Application window, okay. Basically, when you click on the little thing, there's a little thing that says Skyroom is sharing a window, and then if you click on it, all hell breaks loose. So I'm not going to touch it. Can everyone see my screen again?
Yes.
Okay, good. So you can look up this white paper led by Jens Kluba, where all interesting stuff that could be measured, extracted, all sorts of interesting information that could be extracted from the CMB frequency spectrum is detailed. So I will talk a little bit about this in this talk. It's a brief talk, but if you wanted to learn more, you should invite Jens Kluba, who is the worldwide expert on CMB spectral distortions. So I will start by very briefly reviewing the physics of CMB spectral distortions and what are the signals which are guaranteed to be there in the so-called vanilla lambda CDM model. Okay. In part 2, I will remind you that in this vanilla lambda CDM model, 4 out of 4 of the letters, we don't know what they are, neither lambda nor CDM. And so we will talk about how one can probe CDM, in particular if the cold dark matter is some kind of particle that might interact with standard model particles, and so how we can use spectral distortions to look for such interactions. And lastly, I will talk about a somewhat tangential, something that's tangentially related to the CMB spectrum, which is how the monopole temperature influences CMB anisotropy measurements. What is the dependence of CMB anisotropy measurements on the monopole temperature, and whether we can rephrase the H0 tension into a T0 tension. All right, so let's start with a very brief review of spectral distortion physics. And this, you can look at the references listed there to see a lot more details. So the basic picture is as follows. So at redshift greater than about 2 million, photons can be very easily created and destroyed by double Compton emission and Bremsstrahlung. And they are easily thermalized, so they can change their numbers and their energies very easily. As a result, basically, no matter what happens at redshift above 2 million is not going to affect the frequency spectrum of the CMB. The frequency spectrum of the CMB will remain a perfect blackbody spectrum, no matter what happens at redshifts earlier than 2 million. Okay, so if you inject energy at these high redshifts, it could change the temperature, the overall temperature of the CMB, away from some past temperature that you cannot observe anyway, but it's not going to distort the CMB blackbody spectrum. If you then mess up with photons between redshift about 50 or 60,000 to 2 million, so at these times, the photon number changing processes are no longer efficient. However, photon can have their energies, which can efficiently change due to Thomson scattering with free electrons. So photon can diffuse in energy and basically can re-equilibrate in energy at constant number. And as a consequence, no matter what happens, what energy might be injected at these redshifts, the photon spectrum will reach an equilibrium distribution at constant number, which is a Bose-Einstein distribution, i.e. a blackbody spectrum with possibly a non-zero chemical potential mu. This chemical potential can be, so if there is some process that injects energy within a volumetric rate rho dot inch, okay? So this rho dot inch is the rate of energy injection per unit time, per unit volume. So basically the chemical potential is, roughly speaking, the total energy, the fractional energy injected, so the total energy injected relative to the total energy in photons, injected between these redshifts of 60,000 and 2 million. Now, if something happens after redshift 60,000, so neither photon number can change easily, nor photon energy can change efficiently. And so as a consequence, well, whatever happens there will leave an imprint on the CMB spectrum. So if some energy is injected by heating baryons, which is a specific form of energy injection, then there is a universal distortion, which is the Compton Y or Sunyaev-Zeldovich distortion, okay, where this function YSZ in red has a universal form. And the Compton Y parameter, basically the amplitude of this distortion, is going to be, again, proportional to the total relative amount of energy that was injected at redshift below 60,000. But in general, the shape of the distortion resulting from injection of energy at later redshift is non-universal and depends on the precise energy injection channel. For example, if you inject photons with a line or around some broad spectrum, etc., it's not going to be a Compton-Y distortion in general. Okay. If you inject, of course, energy at intermediate redshifts, the distortion is neither going to be a perfect chemical potential nor Compton-Y or something else. It will be some kind of intermediate spectrum. The bottom line is that the fractional distortion in the CMB spectrum, and we're talking again about the global sky-averaged CMB spectrum, is roughly speaking proportional to, up to really number of order unity, the total integral of the energy injected relative to the energy density in photons for redshifts less than 2 million. And now looking at the phi-res limit, which tells us that this number, this fractional change, this fractional deviation away from a perfect black body is less than 10 to the minus 4 or so, this can be translated into some limits on the non-standard energy injected into the early universe at redshifts less than 2 million or so. So let me tell you briefly about 4 signals which are guaranteed to be there. And I'm going to start with this one, where we're going to use the same reasoning later on when I talk about dark matter. So this adiabatic cooling of baryons. So baryons are non-relativistic at a temperature less than MeV for electrons. Okay, so let's consider the time where they're non-relativistic. Their temperature, if they were just decaying, cooling down adiabatically, their temperature would scale as 1 over a squared, where a is the scale factor. So TB dot is minus 2h TB, where h is the Hubble rate. On the other hand, photons, their temperature goes as 1 over a, so T gamma goes as minus h T gamma. Now, Thomson scattering maintains TB very, very close to T gamma up until redshift 200, and both temperatures actually evolve as 1 over a. And so the actual temperature evolution for baryons is T dot is minus h times TB. Okay, so the remainder, this difference between minus 2h TB and minus h TB, is basically the amount of heating per baryon per unit time that the photons provide. So this net heating of the baryons translates to a net cooling of the photons. So the energy injected per unit time per unit volume, this rho dot injection, basically you can translate it as something of order the ratio of number of baryons to number of photons times the energy density of photons, sorry, rho gamma, per logarithmic scale factor interval. Okay, so then if you plug back this into the integral, at the end of the day, what you find is that this process of adiabatic cooling of baryons is expected to distort the CMB by a few times the baryon to photon number ratio, i.e. something like 10 to the minus 9, which is way below the sensitivity of phi-res, and this would require some really serious futuristic spectral distortion experiment to measure, but it is possible that in the future this might be measured. The second guaranteed signal, absolutely guaranteed signal, is the recombination radiation, which was pointed out as early as the 60s by the seminal papers of Peebles-Zeldovich, and this should not be Zeldovich, but sorry, Dubrovich. I messed up the author here. So the idea is as follows: as hydrogen recombines around redshift 1100, there are a bunch of transitions from free-bound transitions and bound-bound transitions that happen. On the left plot, I'm showing you the number of photons emitted per logarithmic redshift interval per hydrogen atom in different transitions. Okay, Balmer alpha, Paschen alpha, bracket alpha, etc., etc. And then on the right plot, this is showing how these transitions are observed today. So they translate to peaks at different frequencies, which correspond to the different centers of these transitions. And these peaks are broad because this emission occurs over some broad range of redshift, as shown in the left. So the current state-of-the-art code is Cosmospec, which was written by Jens Kluba and is presented in this paper here. And so one of the hardest part in this code that was entirely Jens's work is to compute the helium spectrum, which is a lot more complex than the hydrogen spectrum, as shown here. So the bottom line is that this distortion is guaranteed. It can be computed from first principles. We have this code that does compute it, Cosmospec, and it is expected also to be of order the baryon to photon ratio, i.e. 10⁻⁹. A third guaranteed signal is due to the dissipation of acoustic waves. So photons and baryons in the early universe undergo acoustic oscillations, but below the diffusion scale, the self-damping scale, these acoustic oscillations are damped. And this dissipation of acoustic waves dissipates their energy, and this leads to a distortion of the CMB spectrum, basically of order the variance of the photon perturbation on scales smaller than the current, the damping scale at, say, recombination. So if one assumes that on these small scales, which are not directly observed today because they are below the diffusion scale, so they're highly suppressed, if one assumes that the primordial power spectrum is the same as what is observed on large scales, then one predicts that this should lead to a distortion also for order 10⁻⁹. But we can also turn this around and say, well, we can use this to perhaps infer something about the power spectrum on ultra small scales, which are not directly probed by CMB anisotropies, as shown on this plot here. So this is an instance where CMB spectral distortions are a complement to CMB anisotropies. Lastly, this is something that's not at all my expertise, and maybe Colin, who I think is talking later today, I don't know if he's going to talk about this, but one expects, of course, a Sunyaev-Zeldovich signal from the hot intra-cluster gas, and the predictions are this should be a Compton Y parameter on average of order 10⁻⁶, which is just about an order of magnitude below the current phi-RAS sensitivity. So those are the 4 guaranteed signals that are known to exist. But in addition to this, there are a plethora of beyond the standard model processes that could lead to CMB spectral distortions. And so the one I want to talk about is dark matter interactions. So first, if dark matter annihilates with itself, or if its own antiparticle or some other particle. If it annihilates to electromagnetically interacting particles, then it will inject energy into the plasma with a rate which is proportional to this velocity average annihilation cross-section, sigma v, over basically divided by the mass of the dark matter. And this you can just compute it by taking number density squared times mk, and this gives you mass density squared over mk. So then if you plug this into your integral and you plug in the numbers, you can compute this, you can compute what the mu distortion is, and one finds that for an annihilation cross-section of order what is currently constrained by CMB anisotropies, which is this 3 × 10⁻28 centimeter cube per second per GeV, the chemical potential mu is expected to be under 10⁻⁹, so very small. So there's not too much hope in CMB spectral distortions are not very competitive with CMB anisotropies for constant annihilation cross-section, for S-wave annihilation cross-sections, but the story might be different for P-wave cross-sections. And just to illustrate where this CMB anisotropy comes from, and because I made these plots a while ago and I like showing them, so the idea there is that if you mess up the ionization fraction by ionizing the universe more than is standard, then this will translate into an effect on the CMB power spectrum as shown here. So here I'm just adding a bump in the free electron fraction, and you see how, and it's of course a very large bump that does not represent any physical model, but this is just to illustrate how much of an effect this has on CMB temperature power spectrum. Okay, so again, the conclusion here is that for annihilation with an S wave cross-section, we can't expect spectral distortions to be competitive with CMB anisotropies. But, for example, if we consider instead elastic scattering of a non-relativistic dark matter particle with electrons or protons or photons, then we have the same qualitative effect as for adiabatic baryon cooling. Okay, the idea is what? As long as dark matter is thermally coupled to the photon baryon plasma, then the rate of energy injection per log scale factor relative to the photon energy density is basically the number ratio of dark matter particles over photon. And that is something like, this is going to scale inversely proportionally with the dark matter mass. So the lighter the dark matter, the more this signal will be. This is what we pointed out in this paper with Jens and Kamionkowski, with the Klube and Kamionkowski in 2015. And to do this more accurately, as I did this paper I published just last month, to do so more accurately, you need to first solve the dark matter temperature evolution. More generally, you would need to solve the dark matter phase space density evolution. And then from this, you can extract the net heat injection from photon baryon into dark matter. And what's very important, and what we didn't realize in the first paper, is that the residual heat exchange after the official thermal decoupling of dark matter actually matters very much, especially for light dark matter particles, and especially for future experiments beyond FIRAS. So putting this together, this is showing on the left, if you focus on the solid lines on both cases, the chemical potential distortion as a function of the cross-section, say, of dark matter with protons. And so the idea is that as you crank up this cross-section, dark matter exchanges heat more and more with the photon baryon plasma. There is a plateau when dark matter is thermally coupled to the photon baryon plasma through the entire mu era. And this plateau is basically of order the ratio of the number density of dark matter particles to the number density of photons. On the right, if you flip this plot, you can translate any given spectral distortion sensitivity into a sensitivity to a dark matter baryon or dark matter electron or dark matter photon cross-section, as shown on the plot on the right. So what I did in this paper, I'm going to just very briefly go over this, is compute upper limits from FIRAS and make forecasts for the reach of future spectral distortion experiments, which could have, say, sensitivity to chemical potential as low as 10 to minus 8 and minus 9, and ask how low a cross-section could they reach. So all of these plots show, as a function of the mass of the dark matter particle, which I'm afraid is, I don't know if it's showing or not. So I think I forgot to put the axes. I'm very sorry. So the axes are shown here on this top plot. So the plots range from MChi in MEV going from 10 minus 3 to 10 to the 4. So basically, on the left of these plots is a dark matter particle with a keV mass, and on the very right is a dark matter particle with a 10 GeV mass. So basically, this is the bottom line here is that spectral distortions can constrain dark matter interactions, and future spectral distortions can constrain them better than current CMB anisotropy limits on these interactions, and also better than direct detections limits because they can probe different mass ranges in the low mass regime. Okay, and for fun, I also looked at what happens, how one can constrain dark matter with an electric or magnetic dipole moment. And it turns out that if you look at all of the combined constraints from different collider experiments, direct detection experiments, stellar cooling, that spectral distortions would not actually be able to compete for that specific dark matter candidate with the best combined constraints. All of this is available if you want to play with this in a code DM dist, where you can either get the data that I just showed you here for these forecasts and constraints, or you can plug in your favorite dark matter model and estimate the spectral distortions resulting from all the interactions of this dark matter model, including simultaneously scattering with protons, electrons, photons, and annihilations. Okay, so this took longer than I thought. I'm going to try and finish this in 10 minutes. Hopefully I have another 10 minutes. Let me tell you now about this paper led by Misha Ivanov and in collaboration with Julian Leskog on H naught tension or T naught tension. The motivation is what? H naught, the current Hubble rate, and T naught is the current CMB temperature, can both be understood as proxies for how much expansion has happened between recombination, or the last scattering epoch, and today. So, in principle, one could perhaps at least somewhat alleviate the Hubble tension by letting T naught free, rather than assuming, as is done in CMB analysis, that fixing the temperature today as that of Phi-RAS. In principle, of course, Phi-RAS has a very, very high precision, very small error bar. The second motivation of this work was that there were a couple of studies before, but they were somewhat confusing. So they found both at the same time that T naught has a significant effect on CMB anisotropies, but also concluded that it was not measurable from CMB anisotropies alone because of degeneracy. So here, what we did is really clarify very, very clearly, I hope, the precise physical effects of T naught, the temperature of the CMB today, on various cosmological observables in terms of the CMB anisotropies in large-scale structure, and clarify whether it is measurable, and show that indeed it is in fact, in principle, measurable from CMB anisotropies, and why exactly. So to summarize past studies, this is a study by Kluba and Sunyaev in 2008. So on the left, you show the effect on the free electron fraction when you change the CMB temperature, and you see that this is a significant effect naively, which translates naively to a significant effect on the CMB temperature power spectrum. And Planck measures the CMB power spectrum to a sub% precision. So the conclusion of this work was that perhaps one should include the uncertainty in T naught as an additional source of uncertainty in CMB anisotropy analysis. The same year, Hamann and Wang argued that there were some strong degeneracies, in particular of T naught with omega baryon, omega M, and H, and they found that, in fact, the Phi-RAS uncertainty would not affect the Planck error bars. They have not, however, exhibited what are these degeneracies, which is something we're going to explain in detail now. The Planck collaboration in 2015 stated that because of the strong geometric degeneracy, there is no constraint on T naught from Planck data alone, and they used BAO to extract the constraints. And the core collaboration paper said that it is in principle possible to measure T naught, provided one measures the angular scale of acoustic oscillation exquisitely, but that's already the case for Planck, so again, it is not clear exactly what was going on. So in the next few minutes, I'm going to try and clarify what is going on. How do CMB anisotropies depend on T naught? So the standard parameterization of cosmological evolution, okay, is in terms of redshift or scale factor, omega b and omega c. This little omega b, which is big omega b times h squared, etc. Those are all good quantities. It's a good parameterization when you want to describe quantities relative to the present time. Okay, the scale factor is set to unity today. Redshift is 0 today. Now, all physical processes, as we will see in more detail in a minute, actually occur not at a fixed redshift, they occur at a fixed temperature. When recombination happened, it didn't care what happens today. It happened at a given temperature, okay? And physical quantities, constant quantities throughout the cosmic history, this is what I call physical quantities, are the photon to baryon number ratio. So omega b on its own is related to rho b today, but in a billion years, it's going to be a different number. However, the photon to baryon number ratio, or the baryon to photon number ratio, which is proportional to omega b over T0 cubed, that is going to be the same number measured by all observers across cosmic history in all times. And same thing, the dark matter to baryon ratio, omega c over omega b. So as a consequence, when you vary T naught, it is more sensible to use a parameterization where these constant, truly constant quantities are the parameters you vary, and is more sensible to describe things as a function of temperature, baryon to photon ratio, number ratio, and basically dark matter to photon number ratio, if you will, omega c over T0 cubed. Explicitly, this can be seen in the, I'm going to go a little quickly here, but in the expansion rate, you can express this in terms of temperature and show that indeed You can express it in terms of these quantities. Big Bang nucleosynthesis occurs at a fixed temperature and only depends on the baryon to photon number ratio, again, on this parameter omega b over T0 cubed. Recombination, you can show explicitly that the dynamics of the evolution of the free electron fraction XE depends only on the on temperature, because all the transitions, the rates of transitions depend on temperature over typical ionizations of energies of hydrogen. It depends on the Hubble rate through Lyman alpha escape, for example, and it depends on the number density of baryons at a given temperature. So the bottom line is that the recombination history depends on temperature, omega b over T naught cubed, and omega c over T naught cubed. So if you look at the recombination history as a function of redshift, and you vary T naught while fixing omega b and omega c, then you find these huge variations. But if you do the same huge variations in T naught as shown on the left, okay, plus or minus 0.3 Kelvin here, but you fix omega b over T naught cubed, and you fix omega c over T naught cubed, and you show the recombination history as a function of photon temperature rather than redshift, you see that all of the curves collapse in a single curve. Okay? So again, the recombination history only depends on these combination and only depends on temperature. So in some sense, it doesn't depend directly on the temperature today. It only depends on these number ratios. And in particular, the last scattering epoch happens at a fixed temperature, depending on the omega b over T naught cubed and omega c over T naught cubed parameters. Perturbations are usually described in terms of comoving wave numbers k, which are again related to the proper, physical scale today. It is best to work with proper scales at a fixed temperature, for example, 1 Kelvin temperature, in which case you would define this k twiddle as k over T naught. And one can show that in terms of this k twiddle, the transfer functions depend only on temperature, omega b over T cubed, T naught cubed, and omega c over T naught cubed. And if you want to re-express the primordial curvature perturbation at a fixed, as a function of k twiddle, you see that the correct amplitude now is described by as times T naught to the ns minus 1. There should be an ns, there's a typo. All right, so CMB, primary CMB anisotropies. I'm sorry, I'm a little longer than I thought, so I'm gonna try and wrap this up. I'm gonna show you mostly the plot, and I will describe what happens here. So on the right, on the left is the standard fixed, the standard parameterization and varying T naught, and on the right is when we fix these parameters, omega b over T naught cubed, omega c over T naught cubed, as T naught to the ns minus 1, and the angular scale of the sound horizon. And you see that the small scale CMB anisotropies are completely independent of T naught when we fix these combinations of parameters. The large scale variations do change because the integrated Sachs-Wolf effect depends on when, relative to today, was the transition of matter to dark energy domination. And as a consequence, this does depend on what today is, thus it depends on T naught. Another thing that does depend on T naught is the CMB lensing potential. And if you increase T naught, it means that we are earlier in the history of the universe, and that's at everything else being fixed, it means that the redshift of dark energy is smaller and there's less potential decay, so you increase the lensing potential. So the bottom line is that T naught has a direct effect on CMB anisotropies only through ISW and lensing. And so in principle, it is possible to measure it from CMB alone through ISW and lensing. Okay. And we expect a very strong geometric degeneracy at constant theta s, which we show translates to h naught goes as T naught to the minus 1.2, sorry. So let me skip over the gain thing and go to the final plot here. I'm sorry, it took a little longer than I thought. So here we did several analyses with Planck only in green. The standard analysis is Planck plus Firas in red. And we also combine Planck with shoes rather than Firas. And then finally, Planck plus BAU. So the upper quadrant of this plot shows you that omega b over T naught cube, omega c over T naught cube, the rescaled AS, all of these do not care about freely moving T naught or not. The uncertainties are basically completely unchanged. provided, again, you rescale omega b over T naught cube. If you were just constraining omega b, you would see a huge degeneracy. But if you're really looking at the baryon to photon ratio, this is measured just as well when you vary T naught or not, because this depends on the shape of CMB anisotropies. Now, what's interesting is what happens on the lower two rows in this H naught T naught quadrant. So first here, this line here, so Planck measures basically this combination, which corresponds to a constant angular scale of the sound horizon. And the reason that these curves, the green curves, which are Planck only, are so tilted is that they are bounded by the requirement that we want a positive cosmological constant. Okay, so basically Planck alone can measure T naught and can measure H naught, but very poorly. And it wants to get T naught as high as allowed by a positive omega lambda. And why is this? Because if you increase T naught, you will basically have more lensing. And so this increased T naught basically plays the role or replaces this requirement for an additional lensing smoothing. So this unphysical A lens parameter, which we know that is, there's a lensing tension. So you can alleviate some of it by increasing T naught, and this is why these curves are flushed to the right or the left here. Now, so the game we played is replacing in this triangle plot on the left, basically Planck measures the diagonal, Fires measures very well the horizontal, and Shoes measures a vertical line. So really there's a tension that is exemplified as the fact that these three lines do not cross together, okay? And you can replace the H naught tension, which is obtained when you fix T naught as measured by Fires. You can recast it completely as a T naught tension. So you can, again, measure theta S with Planck and use the measurement of the Hubble constant today by Shoes to break this T naught H naught degeneracy, and this gives you the measurement of T naught, which is in 3 sigma tension with Fires. And this is my last slide, I promise. How to break this tension? You can use a fourth party arbiter, which is the baryon acoustic oscillation. This, as shown in blue, is measuring a different kind of angular scale, which is the BAO scale, which is the scale under which the damping length at redshift, some effective redshift, is observed today. And this is a completely different line of degeneracy in the T naught H naught plane. And this happens to cross the same point where Planck alone and Fires alone cross. So the BAO seems to arbiter in favor of Planck and Fires and to disfavor Shoes. Okay, I will leave my conclusions here. I went a little over time. What I conclude about this last T naught H naught paper is we should call it perhaps the Hubble-Penzias-Wilson tension. And this remains to be solved. This is not claiming at all at solving the tension, but rather more of an intellectual exercise, something to make everyone think that, one focuses on one single parameter. There is no really necessarily need to focus on a single parameter, and one should really explore all possible parameters and assumptions in the model. Okay, I'll stop sharing so I can see if there are questions.
Okay, thank you, Yacine. Very, very interesting talk. We have about 5 minutes. 5 minutes. Please raise your hand for questions. No question? Let me ask you a question regarding this deviation in the spectrum of the CMB. Are there any projects in future to measure this 10 to minus 9? I think you said that this deviation from the Planck.
Right. So there was a project called Pixie, which I don't know exactly the current status. I don't know if Pixie was planned to go all the way to 10 minus 9. I think it's more at best and -8. This is my understanding of what the current projects are, but I don't know if either Jens Kluba is in the audience. Jens would be someone who would know exactly what is the current status. My understanding is that there's no concrete, like really super concrete project right now, but there's some push in the community, and in particular, experimentalists are quite convinced that they could, in principle, build experiments with the required sensitivity. The question is, how do you deal with foregrounds? Is it worth building an experiment if the only guaranteed signals are, most of them are very, very small? I think that's the reason why there hasn't been yet more spectral distortion experiments. There are too few guaranteed signals, but there are lots of beyond the standard model signals, so that could be interesting.
Any question? Well, I had an, okay, Shant, please go ahead.
Okay, Yacine, thank you very much for a very interesting talk. So there's a statement in the previous talks that that the BAO does not measure H0, but the combination of the H0 and the sound horizon. In this sense, is it logical to say that H0 tension and T0 tension are completely equivalent or not?
So you say the BAO does not measure, as shown here. So the BAO, you see my mouse? Yes.
Yes.
So indeed, the BAO mostly measures this combination, right?
Exactly.
So in this plane here, I'm gonna try and move it so I can see it. So in this H0 T0, so what I really skipped over, I didn't have time, unfortunately, but the theta S for the CMB, you can express it as a function of H0 and T0. And if you say I have a constant theta S, I get this line. And if you say I have a constant theta BAO, you get this other line, which happens to be, kind of orthogonal in this plane. So I don't know if I'm answering your question, but yes, the BAO does not measure. The BAO measures this specific combination here.
Right.
This angular scale.
I mean,
just like the CMB measures mostly angular scale, does not measure H0 directly. The CMB measures H0. We think it measures H0 only once you have imposed this very sharp wire on T0.
Right.
And the same is true for the BAO.
Right.
Okay.
Okay, thank you.
So I had another question. You mentioned that the chemical potential for in your figures, is it associated to the chemical potential of the dark matter, or you consider it for the photons?
This is just whenever I talk about chemical potentials, I talked about the photon chemical potential. Yeah.
Mm-hmm.
And whenever I talk about dark matter, I assumed that the dark matter number is conserved and is given by whatever we observe today.
So you consider non-equilibrium thermodynamics in your calculation, I guess.
So yeah, dark matter can be in thermal equilibrium in terms of the temperature of the dark matter. Initially can be in equilibrium with the plasma, but I consider that it's no longer in chemical equilibrium for all the calculations involved. I haven't specifically considered the generation of dark matter number. I assume that it's given already, has already, say, been produced, whichever way it has been produced. Then perhaps its temperature can be in equilibrium, but its number is already fixed. This is what I've been assuming.
Okay, thank you. So I think there is no other questions. So let's thanks again, Yacine, for an interesting talk. So we are virtually clapping here.
Okay, thank you for the invitation. And if you have questions, feel free to email me. It was a little bit fast. So.
Okay, thanks so much. So the next speaker is Luke Hart from University of Manchester.
Yes, just Sohrab, thank you. if you agree, let's wait maybe for 2-3 minutes. That then people can decide to be in this room or.
Okay.
Puyan, can you just pin? Yes, exactly. And you can go to the room number 2 for the parallel session. You have the program on the website, but it's more for us, for organizers and presenters. Please be sure that you are not in 2 rooms because then there is an echo. Okay, so let's. If you agree, we start in 2 minutes. And for your information, the talks in this room will be live streamed on YouTube, and room 2 is live streamed on Apparat. And at the end, we will put all the videos on YouTube.
Okay. I wonder if you save these videos or they're.
Yes, we record the videos. Yeah, and yeah, I mean when we live stream on YouTube, it's automatically recorded. So.
Okay. What about Apparat?
No, Apparat can do that, I guess, but we record the Apparat. I mean that room separately.
Okay.
Is it true, Puyan?
Yes, we're recording all of them.
Good. And when you are ready for the live stream for the room number 2, then let us know. Then we can start.
Okay.
Please.
I would like to ask Luke if you please raise your hand, then we can.
Yes, let me.
Okay. So maybe you start to just share screen and then.
Hello.
Run.
Can you hear me?
Yes. Hi.
Hi. Right. Okay. Yep. Okay. Okay. Yeah.
Yeah, we can see it.
Okay. Just give me 1 second. Okay. Right. Okay. Cool. So I'm ready to go. You want me to? I'm cool.
Nima, can we start now?
Yes, I guess so. Puyan, are we ready for live streams? Everything.
Yes.
Okay. So, yes, Sora, please.
Okay. The next speaker is Luke Hart from University of Manchester. He's going to talk about reading between lines, the hidden secret of the recombination. Thank you so much, and please.
Brilliant. Okay, so yeah, firstly, thank you for having me. Give me a shout if you can't hear something or if my sound's awful. But yeah, no, really thank you for accepting my talk. It's been really nice to hear about what's been going on, and I'm hoping that I can give you something really interesting in the form of this talk about recombination. Yeah, so I'd just like to start as I think would make sense, just to give a quick overview of where I'd like to go with this talk about this hidden secrets of recombination. Yacine actually sort of did a bit of the legwork for me by discussing this recombination stuff in his talk, and I'll allude to that a little bit later on. But I'd like to talk about the physics of recombination very briefly and why it incentivizes where the recombination radiation fits in. Number 2, I'll be talking about this recombination lines, these lines we're supposed to be reading between, which are, conveniently tucked away behind the last scattering surface, if you will. And finally, whether or not we can do any cool cosmology with these lines when we can detect them. And that's where this play on the words, the read between the lines, comes in. Okay, so first off, recombination, just as a cartoon depiction, I like to show this idea that electrons and protons are interacting in this thermal bath at equilibrium before the majority of recombination, where the electrons are bouncing in and out of these bound states with hydrogen and helium nuclei. And then eventually the universe is expanding, obviously. There's the Hubble expansion rate starts to overtake these interaction rates within the atoms. And then finally, if you look on the right-hand side here, you can see that the protons and electrons start to bound into these bound atom states of hydrogen and helium, and the photons can no longer interact. They're too low temperature, and that's where the free streaming comes in. And I've put an asterisk next to irreversibly there because, of course, we know long-term, spoiler, it's not really irreversible because we have reionization going on. And just to sort of quickly just hone in on the fact that this process in the middle here has taken a lot of people, a lot of time, and a lot of work, you know, and it was vital to get the sort of precision we need on for Planck's sort of Planck data and Planck estimates of the recombination model, as it were. Okay, so if we just take this very naive idea of a 3-level atom where you have a ground state, an excited state, and this and you approximate all the other states as the continuum. I'm just giving this sort of 101 picture of recombination because it will fit later on in the talk. So direct recombination is sort of hindered because there's immediate reabsorption of the photons by all the other sort of baryons in the fluid. Lyman alpha transition is very possible, however, as something which Yacine very vaguely alluded to in his talk. You get this sort of resonance scattering where the Lyman alpha photons get trapped as they start to interact with other atoms as well. So this becomes a less efficient method of recombination, and you get this thing called 2-photon decay, or should we say sort of n-photon decay, where these you get multiple quanta from the 2s state down to the 1s state or the 3s state and so forth. And these would be forbidden in the lab, but in recombination, at the time of recombination, this is the dominant mechanism for this process, and it's really, really interesting. So a lot of people, as again, I say Yacine's done a lot of the work for me. We use this X measure to sort of say how the number of species in these different states over the total number of atoms, hydrogen and helium, and this XC measure at the top left here is how we measure the relative ionization of the recombination fluid, and this can be approximated by some sort of these ODEs. And I wanted to very briefly just show this. I don't like showing maths in slideshows, but basically so you can see that in this C coefficient here on the left, on the just after the equal sign, the 2-photon and the Lyman alpha physics is encoded in that, whilst the recombination and the photoionization physics is encoded in these relative coefficients, which sort of weigh up these two seesaw components of the master equation going on at recombination. And then finally, to just say there's all this extra physics as well, which has been studied copiously for say like 10 to 15 years. And all of these need to be keenly paid attention to. And when you include the whole picture of recombination, you get something which looks like this, the ionization history, where in the early universe, this is very high because there's loads of ionization. So at earlier times on the right-hand side, high redshift, you have a lot of free electrons which tail off to a low amount of free electrons, and that's the process of recombination. And just to quickly emphasize here, this little orange curve here is just the disparity between the trivial ODE system in like something like RecFast and what you would expect with a more sophisticated recombination code like CosmoRec or HiRec, which builds on these principles of the multi-level atom, detailed treatment of helium recombination, and radiative transfer. And they're both covered by the codes CosmoRec and HiRec, which were written by Jens Kluber and Yacine, who you just heard from, respectively. And these are the websites. You can get hold of the slides afterwards if you'd like to play around with these codes. They're a lot of fun. Okay, so why have I spent like a crash course of recombination? Well, to analyze how the electron states are constantly fluctuating and things, we need to trace exactly how different energy levels are populated to work out how the ionization history is evolving. But in these sophisticated models in HiRec and CosmoRec, that actually really keenly relies on the evolution of the photon field so that you can model the temperature fluctuations of the underlying CMB. And so what if we were to turn our attentions away from what's going on with the actual free electrons, which contribute to the CMBs and isotropies, and what if we were to focus, say, on how those perturbations to the black body spectrum were being implemented due to the non-equilibrium processes in recombination, and they were depositing energy into the CMB's black body. And when I say I'm talking about perturbations to a black body spectrum, so of course everyone's going to start hearing what we heard about before, which was CMB spectral distortions. And so these are these processes where you have this non-thermal process due to various photon number or photon energy altering processes like the ones that Yacine's just mentioned, which can give rise to these various distortions. You've got the mu distortion and the Y distortion there across time. And if you want to hear a little bit more about the mu distortion, we'll be hearing a talk from Tom Kite on how gravitational wave background could influence the mu distortion. Obviously, you heard from Yacine and how dark matter interactions can generate these sort of distortions as well. But the one that gets less attention is this one in the middle, which is due to the recombination signal, the depositing of energy into the CME's black body due to these various interatomic transitions going on in recombination. And so this is what the recombination radiation looks like. You've got this sort of superposition of hydrogen and helium lines here, with helium being sort of an order of magnitude lower, because the helium recombination is just essentially that much fainter. You get these redshifting of effective energy lines, as Yacine was mentioning in his talk, and these really unique spectral shapes coming from these two species of recombination. So this is all affected by the background cosmology. So could we constrain some cosmology? Could we get some cool constraining power with this idea of this probe, if we could get the experiment to do it? And the answer is, well, yeah, maybe, because if we, as was shown in this work that I did with Aditya Rotti and Jens last year, you can actually look at how different cosmological parameters affect this recombination radiation. And the biggest take home from these two plots here is this derivative is weighted by the amount of change to the given parameter. So the higher the response is, the more detectable a change would be if you had an experiment to try and look at this. And there's some really cool physics going on. So the general amplitude of the recombination radiation goes up if you increase the number of baryons, therefore increasing these non-thermal occurrences, which will deposit energy into the CMB. Cold dark matter and N-effective have very similar traces, these two pink curves, because they both enter through the expansion rate. And then the two photon decay of hydrogen and the primordial helium abundance are examples of parameters that can probe hydrogen and helium recombination uniquely. And so that's kind of really interesting as well. And these are just these highlighted 5 parameters are the ones that we included in our Fisher analysis, which I'm about to explain. So on this graph here, you can see all the different foreground components and the foreground contributions, which you need to account for in your spectrometer mission if you're going to propose an experiment. And you can see that these all have very smooth spectra, whereas the CRR has very unique spectral features. And so if you can get a spectrometer down to the sensitivity of this recombination radiation, you can almost sort of detach the foreground signals away, and you won't have any of this interaction within all of these independent channels in the CRR, because it's got this weird and wonderful unique spectral signature. And just to show you here, Pixie, SuperVix, Pixie, and some futuristic spectrometer sensitivity curves have been shown here as well. I can go back to that if anyone has any questions. And then you plug this into the Fisher, and then you can forecast for how detectable these parameters would be, and that's what we did in this paper. And the bottom line, I mean, there's a lot of information on this plot. I don't have enough time to go through it, but the bottom line is that if you can get a sensitivity down to, say, sort of 5, 6 to 10 times more sensitive than what is proposed in Voyage 2050, you can start to get some really interesting constraints, particularly on the primordial helium fraction, which is slightly less constrained with CMB anisotropies. And this is something really exciting coming from the future. So yeah, I mean, I like to say that the recombination problem is done, but it's not dead. You know, the atomic physics at the edge of the universe is still really interesting. There's lots of juicy cosmology going on there. And so using all of this spectral information, hopefully we can start to isolate some of the physics going on during helium and hydrogen recombination independently and get some more information there. So thank you very much for listening. And as I said, any questions are welcome.
Thank you, Luke. Let's thank Luke. Very nice talk. So, question, please. Please raise your hand.
I almost think it's worse when you have no questions.
Okay, I had a question about this spectral line that you showed for the heliums. What kind of information you can get from this line? I mean, we know that yeah.
You mean this one here? Or?
Yes, this one. So assume that let's imagine that we can measure this spectral line on the CMB. So what kind of information, extra information, I should say? Yeah.
So what you've got to remember is that the actual detection of this distortion, it will look like a superposition. So it will look like hydrogen and helium are sort of mixed in together. The really interesting thing about helium is that because of things like the feedback mechanism of helium into the hydrogen recombination and things like that, if you start playing around with helium recombination, you'll start noticing whether or not these absorption features start to create little divots and things in the total recombination radiation. So currently what we've investigated so far is that the majority of any of this helium change will come from things like the most constrainable change is something like the primordial abundance of helium. You start playing around with that, that plays around quite densely with helium recombination. But if you start including, so we're currently looking at say some models that meddle with the expansion rate during helium recombination independently of hydrogen recombination, and how that would then play around with the helium lines and the helium absorption features independently of the hydrogen recombination epoch. And so, I mean, I've had a little chat with, so I work with Jens, and we had a little chat about this before. And one of the things that I've been working on quite a lot is whether or not you could do this with the very popular model of early dark energy, for example, because if you can generate a model that creates a sharp enough dilution of the field that it doesn't affect hydrogen recombination but affects helium uniquely, you can get something that would change this helium distortion on its own. So that's just an example, but yeah, that currently published, we've looked at the helium abundance, but we are looking at more sophisticated expansion models as well.
Okay. I saw that Jens raised his hand.
Did he?
Can you please just click on the yes?
Oh, can everybody hear me?
Yes.
Oh, great. Yeah. Sorry, the first time that I'm raising my voice, so let me just make sure. I wanted to maybe just quickly add there. One of the unique things about measuring the helium distortion or contribution is, of course, that this is really the most pristine pre-recombination or pre-stellar measurement of the abundance of helium you could ever hope for. It's essentially going really directly to the primordial helium abundance, and so this is actually, just from that point of view, also a very, very interesting aspect. And then remembering as well that these recombination lines, the limit coming from cosmic variance, again, we're talking about principle here, is there's no essential limit on measuring these kind of distortions to very high precision, because everything that will come in standard cosmology as a perturbation to this will be at second order in the variation of the densities across the universe. So you have really the opportunity to measure many of these parameters very, very precisely just by looking at the absolute calibrated sky. This is very challenging, but as Luke was saying, even with foregrounds, there is, because of the uniqueness and featurefulness of this signal, you can in principle hope to actually distinguish this from many astrophysical foregrounds. So if you, for example, compare, just to close, this with measurements of the mu distortion, they are sensitivity that will get you a very, very good measurement on mu, will get you a very, very good measurement on the recombination lines, although the recombination lines are actually an order of magnitude lower than the mu distortion. But the mu distortion is much, much smoother, and therefore the penalty by foregrounds is much higher. So that's really interesting as well. So just a few comments there. Thank you.
And okay. Oh, sorry. I should turn off my microphone. That was turned off. Thanks so much for look for interesting talk. And okay, so let's thanks again virtually. And our next is Sunny Vagnozzi. Hi.
Hello everyone. I'm Sunny Banihashemi from the University of Cambridge, and today I will be telling you about recent discussions concerning spatial curvature in relation to the Planck results. and possible ways to get model-independent constraints on curvature from cosmology. So to dive into my talk, we know it's true that the Planck results from CMB temperature and polarization data appear to prefer a spatially closed universe. However, to get a reliable constraint on spatial curvature, we must combine Planck with external data to break the geometrical degeneracy in a reliable way. And reliable is the key word here in my talk. It's going to be related to tensions between data within a curved model. And if you manage to do this, what you learn is that the universe is indeed flat to the 10 to the minus 2 level. And I'm going to also present a way to get model-independent constraints on curvature from cosmological data. So as far as the CMB is concerned, a lot of information is contained in the position and amplitude of the first peak. This is a very zeroth order approximation, but it's useful to understand the geometrical degeneracy. Now, imagine the following situation. If you look at this person in front of you, from this picture alone, you can disentangle how far this person is and how tall they are, simply by looking at the angle subtended by the person. And it's pretty much the same if you think of the first peak of the CMB. You only have access to the acoustic angular scale, and you can't disentangle at the same time the size of this feature, the acoustic scale, and how far it is from you. To disentangle the two, you need some reference between you and this person, or between you and the CMB, such as these trees I've put in this picture. Now, mathematically speaking, in order to break the geometrical degeneracy, what you want is some probe which is able to pin down the late time post-recombination expansion rate. So basically the denominator of the acoustic scale. If you want to think of this mathematically, it's like closing an underdetermined algebraic system. And the way to do this is by either measuring distances or expansion rates in the late time universe. And there are many ways of doing this. One way, which is well known, is to use BAO measurements of the distances and expansion rate. And BAO are in fact very similar to the analogy of the trees I made in this previous picture. But there are other ways, of course, of breaking the geometrical degeneracy. You can use the CMB lensing potential power spectrum. You can use supernovae. You can use local H0 measurements, and so on. Now, if we look at what Planck data alone says, using the Plick likelihood with this caveat, you get this surprising result that there's an apparent 3 sigma detection of non-zero spatial curvature. Now, the reason why you have to be skeptical about this result is not so much the non-zero curvature in itself. It's the fact that within this 7-parameter lambda CDM plus curvature model, you infer rather implausible results for the Hubble constant and the meta density, as you see in this table on the right-hand side. And these values are pretty much excluded by any other independent probe you can think about, like local H0 measurements, or strong lensing measurements from Holy Cow, cluster counts, F-gas measurements, and so on. I won't go much into the details of where this problem comes from. It suffices to say that it's related to the A-lens internal tension, in quotation marks. But what's interesting is that other analysis, for example, based on a modified version of the CAMSPEC likelihood, or independent measurements from the Atacama Cosmology telescope, appear to support the interpretation that this preference for a closed universe from Planck might be a possible fluke. Now, nonetheless, it's still important to investigate it further, and in particular, break the geometrical degeneracy in order to get a more reliable constraint on spatial curvature. One way to do this is, as I mentioned previously, to use BAO measurements, and then you get these contours on the left, which push you towards a spatially flat universe and towards more reasonable values for H0 and omega m. A closely related way of doing this is to use, instead of only the BAO information, the information on the position of the BAO wiggles, to use the full-shape galaxy power spectrum information, as we did in this recent paper in October. And of course, BAO and full-shape power spectrum should give you similar results, which they indeed do. Also, the full-shape power spectrum brings you towards a spatially flat universe, as you would expect. Now, the problem, which you can clearly see by eye, is that there is a tension between Planck and these other external measurements in the context of a non-flat universe. You can clearly see there's a 3 sigma tension by I here. This was nicely quantified in this paper by Will Handley, where he showed that Planck is in tension with many external probes within the context of a non-flat universe. So the question is, should we believe results which come from a combination of data sets in tension within a given model? And in my opinion, even though these external measurements are important to break the geometrical degeneracy, we cannot believe results which come from a combination of data in tension. If I go back to the previous heuristic picture of how to break the geometrical degeneracy, it's like trying to infer the distance to this person using references from a fantasy world, which do not really tell us anything. So we are sort of at what I call an impasse or a stalemate. And in my opinion, the way out is the following. We need to find what I call a golden data set, which allows us to break the geometrical degeneracy while not incurring in strong tensions with Planck. And one minor point is that ideally this golden data set should be as model independent as possible. And the reason I say this is because certain measurements, such as BAO and full shape galaxy power spectrum, carry implicitly some assumptions. One has to make some fiducial cosmological assumptions when during the data reduction process. So one possible candidate for a golden data set are cosmic chronometers. And the idea is basically to invert the age redshift relationship in a FRW model. And if you can find a tracer for which you can reliably measure the differential age evolution as a function of redshift, what you can do is measure the Hubble rate at redshift other than 0. And the trick here is to use massive, early, passively evolving galaxies. If you do this and combine these measurements with Planck, you find a result which is consistent with spatial flatness within 1 sigma at the cost of a much milder tension compared to previous results. And another interesting thing is you can do this also with uncalibrated Hubble flow supernovae from the Pantheon sample. The only caveat is these results are true within a 7-parameter model of lambda CDM plus curvature. The moment you free up the dark energy equation of state, you move towards a phantom closed universe. And I think this is worth investigating further, but I won't discuss it anymore here. And finally, let me address the final question of my talk, which is whether we can obtain model-independent constraints on curvature. And the trick is the following. Let's focus on the uncalibrated luminosity distance, h0 times dl, which is essentially what uncalibrated supernovae from the Pantheon sample, for example, measure. Now, if you can get an independent measurement of the unnormalized expansion rate E of z, which determines this integral here, then once you have these measurements of the uncalibrated luminosity distance, you can directly infer curvature. That's the only remaining parameter connecting the blue and red quantities. So what we do is we take cosmic chronometer measurements. Essentially we do a Gaussian process regression to get the unnormalized expansion rate. So what we really do is we sample the curvature parameter, h of z, and the Gaussian process hyperparameters, and all together, and then we infer curvature from the combination of cosmic chronometers and Hubble flow supernovae without assuming any cosmological model. And we find, of course, results which are much looser than the others I've shown you before. We find cosmic curvature to be consistent with spatially flat case within 1 sigma. In fact, we find 0.02 plus or minus 0.25 for omega k. And with future supernovae data, this can improve to about 0.03, so by 1 order of magnitude. So this method, of course, delivers results which are weaker than other ones, but I stress again that these are model independent, so they are, of course, valuable. So to conclude, it's true that Planck data prefers a closed universe at face value, but to get a reliable constraint on spatial curvature, you must combine Planck with external data to break the geometrical degeneracy, possibly without incurring in tensions. And you can do this with Hubble-flow supernovae or cosmic chronometers. And when you do this, you learn that the universe is spatially flat to the 10 to the minus 2 level. So if there's a one-sentence takeaway message from my talk, that's pretty much it. And finally, you can combine cosmic chronometers and Hubble-flow supernovae in a model-independent way to infer curvature without having to assume any cosmological model. So that's pretty much all. And I look forward to these discussion sessions in the conference. And I thank the organizers again for inviting me to give this talk.
Hello, everyone. I'm Sunny.
Thanks so much, Sunny. Can you please turn on your, yes?
Yeah, you can see.
Excellent. Excellent. Let's thank Sunny. Sorry. Excellent, Pat. Well, Adam has a question. Please turn on microphone for Adam.
Can you hear me?
Yes, Adam, yes.
Okay. Very nice talk. I enjoyed it very much. I guess the one quibble I would pick, but it would be a fairly significant one, is you talked about this effort to do a very model-independent way of breaking the degeneracy. I must say cosmic chronometers are far from model-independent. They're not dependent on the lambda CDM model, but they're dependent on what I think is a much more complicated model than lambda CDM. I mean, you have to understand the star formation history of the galaxies you're looking at. You have to do the stellar population synthesis calculations. You have to assume the IMF, the initial mass function, and you have to account for selection biases in redshift surveys to know if you have really the most massive galaxies. And I think people are only just beginning to really quantify the systematic uncertainties in this. I think there's this paper by Moresco that has begun doing that. But so I guess my question to you is it really model independent what you're proposing? And is there a more model independent way to pursue it?
Yeah, that's a very good question. So of course, yeah, your quibble is totally correct. Whenever I say model independent, I was really meaning cosmological model independence, not astrophysical ones. You're totally right about worrying about this astrophysical model dependence. What I can say is you correctly pointed to the works of Moresco et al., who was also an author of my paper. What he has been doing is basically, loosely speaking, trying to marginalize out this model uncertainties in astrophysical space. So basically averaging over different star formation history models, SPS models, and so on. There's actually, in my paper, we discuss what's the effect of including these systematics in the analysis of curvature. And indeed, you find that your error bars blow up a bit, as you would expect. I think the work of Michele and others is moving towards the direction of more precisely quantifying this possible astrophysical model dependence. And we haven't gotten there yet, but I think we're getting there. So of course, all my results are contingent on whether or not we believe cosmic chronometers. But on the other hand, as I showed, you can play the same game with Hubble-flow supernovae, which I'm sure you're very familiar with. And I'm sure there's no cosmological model dependence in your analysis, and at least very weak astrophysical dependence at the same time. I'm sure you can confirm that.
Yeah, I mean, I think that's the right approach, is trying to quantify the astrophysical model space and then propagate that as systematic uncertainty. So I agree with that. I mean, the type 1a supernovae, it's completely empirical the way they're used, and so doesn't formally have that astrophysical uncertainty because it doesn't use a model space. But thanks for your answer.
Thank you for your very good question.
Thank you. And Marika?
Thank you for the nice talk. So my question is about the omega K tension and how you were saying that we need to break degeneracy. Now, from the plots you showed, it just looked like that. The only reason when you combined with, say, the some of the data that didn't have much tension with Planck was that those data weren't as constraining as, say, the BAO or something like that. I don't know if you have looked at this, like because if Planck by itself is excluding omega k equals 0, let's just assume that, then surely whatever data you add to it, it's not going to bring the omega k back to 0 without being inconsistent with Planck, basically. So it's not possible to get that.
Yeah, that's a very, very good question. So I think there are two answers to the question. Okay, so Marika said something completely correct, that since Planck appears at face value to prefer a closed universe at so high significance, there's no way you can go to a flat universe without at least a bit of tension. That's completely true. So you can quantify the tension. There are various measures. We've looked at one in particular, which indicates that the tension between Planck and BAO is strong if you assume a curved universe, but it's only mild if you consider, say, Planck versus Pantheon or Planck versus chronometers. And so in my opinion, the real question is, what's the threshold for one trusting a certain combination? So I think the threshold is reached for, say, Planck plus chronometers or Planck plus Pantheon. The other question is, okay, you say certainly the tension is being reduced by virtue of the larger error bars. This is partially true. I don't know if you could see it in the plots, but the error bar for, say, Planck plus chronometers is actually only a factor of 2 larger than Planck plus BAO. So it's not a huge change. It's enough to reduce the tension by an important amount. Another aspect is not only the error bar, but also the central value. It so happens that if you take Planck plus BAO in a curved universe, the central value is actually more towards an open universe. I think it's something like 0.002 plus or minus 0.003. Whereas if you do the same for Planck plus Pantheon or Planck plus chronometers, the central value is more in the ballpark of a closed universe. So it's a combination of central value and error bars larger by a factor of 2, which makes it so that the tension is much milder, to the point that you can actually start to trust the combination. I hope that makes sense. That was a very good question, by the way.
Yeah, thank you. Just out of curiosity, can you combine the other data, not with Planck, to break degeneracies and get omega k?
Yeah, of course. You can do it with... I mentioned a few. You can use the full-shape galaxy power spectrum, but that's sort of a very close cousin to BAO. If you do that, you're mostly using the BAO information in there anyway. You can use CMB lensing, reconstruct it from the temperature 4-point function. You can, in principle, use local measurements of H0, but there, you have a huge tension greater than 5 sigma, simply because, as we saw from Eleonora's talk before, in a curved universe, you actually worsen the Hubble tension. Okay?
Yeah,
so
no, I meant if you exclude Planck data. So.
Okay.
That you discuss in the break time.
Okay.
Okay, thank you. So thank you, Sanif. Very interesting talk. Our next speaker is Abdolali Banihashemi from University of Shahid Beheshti. Let's thank Sunny again. Abdolali, are you here? Okay.
First, I want to thank the organizers. Okay, first, I want to thank the organizers for accepting my presentation. I'm going to talk about a model in which dark energy emerges as a critical phenomenon. Let me first start with lambda CDM, which is very simple and very successful. We have checked it over and over, but recently some odd features in data have showed up. The most famous one probably is H0 tension, which I guess is a very good hint for modelists to find a new physics beyond lambda CDM. Let me explain the story behind our model. First, we thought that H0 tension is a temporal tension. It's the discrepancy between early universe and late universe. So perhaps a dynamical dark energy can be a solution to this tension. But we wanted a reason and a motivation behind such a dynamic. At the same time, we were amazed by the fact that phase transitions provide a natural way for systems to change their properties like density. So we thought maybe this phase transition is a good motivation for dynamic in dark energy density. Phase transitions are categorized under the literature of critical phenomena, and we are all familiar with phase transitions examples. They happen in any self-interacting many-body system because of change in external variables like temperature. And we know that our universe has been cooling down ever since the Big Bang, so maybe dark energy is sensitive to this change, and it has undergone a phase transition in its history, and we should consider it. But how are we supposed to deal with such an unknown system, because we don't know the microphysics of dark energy? The good news is that all phase transiting systems are similar and behave similar, at least at phenomenological level, and we can treat them very generically, thanks to Ginsburg and Landau, who at 1950s introduced their effective free energy, which was in terms of this order parameter, which is denoted by phi here, and their free energy consisted every term respectful or every term compatible with the symmetries of the system. For example, if the system had Z2 symmetry, you shouldn't include this phi cube term or this term which is linear in phi. And here this T plays the role of external variables, for example temperature, which is defined here. Equipped with this formalism, we came up with our model, which was critically emergent dark energy. We suppose that our dark energy has an order parameter, phi, and the density of dark energy at background level is just the spatial average of that order parameter. Also, we assume that the free energy of that order parameter is respectful to Z2 symmetry. And also, we assume that the external variable is proportional to 1 plus Z, and also we worked at mean field approximation at first step. By demanding a stationarity of free energy with respect to phi, one can obtain the equation of motion for phi, which at mean field regime yields to this expression, and also flatness fixes the coefficient m over lambda, and so we have the density of dark energy as a function of Z, and by plugging it into the continuity equation, we have its equation of state, which is always phantom-like in our case. As for the confronting our model with data, we have one more free parameter with respect to lambda CDM, which is a critical scale factor. This scale factor is the time at which transition happens. We first used Planck CMB data, and then after we saw that the tension is not present in our model, we happily added our 19 data point. Here you can see the contour plot of critical scale factor versus H0. You can see that when the critical scale factor is very low, the H0 is very low, and that's because our model in this case reduces to lambda CDM. But in our parameter space, there is a region which corresponds to higher values of critical scale factor, and within this region there is no tension with our 19 data point, because you can see that our 1 sigma contour touches the 1 sigma band of shoes measurement. And so we can add the R19 with no worries, and that will makes our contours closed, and the lambda CDM is not favored by data anymore. Here you can see the fractional density of dark energy. The dashed line is for lambda CDM, and the red band here is for our model, is 1 sigma of our model when R19 is not included, and you can see here that our model includes lambda CDM, but when we add R19, the lambda CDM is not within our model anymore. And here you can see that when we have R19 or when we don't have R19 in our analysis, the contour plots overlap within 1 sigma region. So this means that the tension is absent in our model. But this is not the end of the story, because in principle one can go beyond mean field regime by keeping the nabla phi squared in the free energy. Doing so will result in situations like this. Here you can see 4 stages of simulated universe within our model. When the temperature is high, you can see these black and white colors, which represents different order parameter of dark energy, are distributed very randomly, but as the universe cools down, the correlation length grows, and finally below the critical temperature, 1 order parameter gets dominant. And these dark energy patches of same order parameter or equivalently same density, these black or white patches, imply a lot of interesting features, and we are very interested in them because lambda CDM also suffers from spatial anomalies. For example, CMB at large scales is not consistent with the small scales, as you can see in Planck paper. One can avoid this tension by either relaxing omega k or relaxing amplitude of lensing. But relaxing the omega k will result in a closed universe, which is in crisis because, as discussed in this Nature Astronomy paper by Di Valentino et al., because then the CMB is completely incompatible with other observables. And varying the amplitude of lensing is meaningless and unphysical. Also, in either these cases, one encounters with the tension with CMB lensing data points, which you can see here at high L's. We are right now investigating CMB lensing within our model, and you can see here the a typical result that I have plotted here. This solid line is for our model, and you can see our model predicts higher values of lensing potential at low L, and at high L's, where the CMB lensing data prefers the lambda CDM values, our model also predicts the same values as lambda CDM. So this is rather promising for our model, and we are investigating if we can we are capable of resolving the tension between high L and low L or not. Also, CMB suffers from power asymmetry, and we think that although it's very odd in lambda CDM model, it's not odd anymore in our model because we have a long wave mode of dark energy density, as you can see here. I mean, when the temperature goes down, 2 big patches form in the universe. Each of them consists of same order parameter, and this long wave mode has effects on CMB photons through ISW effect, and this can potentially explain the power asymmetry of CMB. Thank you for your attention.
Thanks so much, Abdolali.
Okay, first I want to thank the organizers for accepting my presentation.
Okay, let's thank Abdolali. Excellent talk.
Thank you.
Bye. Well, let's have questions. Marika, you have a question?
Yes, thanks for your interesting talk. I wonder if you've looked at what happens to the value of S8 with Planck under your model.
Yes, the value of sigma 8 is higher than lambda CDM, but because that happens with a lower value of omega matter, we have almost the same S8 as lambda CDM. I guess.
Yeah. Does it will it affect any of the late universe physics?
Yes, it's phenomenologically very like phantom dark energy.
Okay.
So, yeah.
So you have to do a simultaneous analysis. I guess you have to apply it to say large scale structure data as well. You might get a different S8 from them.
Yeah, you should do that.
Yeah. Thank you.
You're welcome. Thank you.
Okay, any question? Well, it seems there's no question. Let's thank Abdolali again.
Okay, thank you.
Thank you so much. We are clapping virtually. Well, I do it. Yeah. Okay. So we've finished the first this part, and then the next part of talks will start after 25 minutes. Okay, we will have a break now. Thank you.
Thank you, Sohrab. Thank you very much. And thanks all the speakers. Thank you. Hi, Mike. Can you raise your hand, please? Okay, great. So you should have a microphone. Do you see the microphone symbol on top right?
Yes, I do.
Okay.
Can you hear me now?
Yes, great.
Okay.
And okay, we can. I guess you wanted to share your screen, no?
Yeah, I do. Let me just rearrange my windows for a second or two so they're in the optimal configuration for this.
Okay.
Too many tabs. Hang on. This to get these problems out of the way when there's nothing else going on and not everybody's waiting. I've made that small, so now here we are on this screen. Okay, that's good. Okay, so I guess I turn on my camera. Yes. And it wants to get permission. This is on Firefox. Okay, that's good.
Great, yes. We can.
And now if I press this, I guess I get the screen sharing
yes.
Here. Share select window or screen, and I have to choose it by its title. It's interesting because what is this one? Is this one called? Hang on a second. It should be called Keynote. Should be called Keynote, but it's not actually appearing on the list. Hang on 2 seconds here. Let me close everything else down that I don't need, so that I only have Keynote running. Close everything else. Then I don't have any windows to get confused by. That's interesting. It's still not okay. Let me give me a couple of seconds to literally shut everything down.
Oh, take your time. We have enough time.
Yeah, exactly. That's the good thing. You got time to figure it out. Zoom I don't need because we're not on Zoom. Acrobat I need. Now I only have Keynote. If I load up the talk, it should appear here in theory. It's interesting because the list of screens is still the old one. So somehow it's not refreshing. Let me try unsharing it. I'm going to allow it. I don't know which one screen one is. I got 3 monitors. No, I don't think I want screen 1. I maybe want screen 2. That would be that. I could share it on a screen by screen basis, which might work. But if I play that in a window, I have to put that on top, I guess. That shows the extra stuff. So let me just turn this off for a second. I'll turn it back on again.
Okay.
Stop sharing. I'll see if it recognizes it if I restart it when it's already open. That looks more promising now. It's showing the actual screen. Okay, that's good.
Yes, so great. Do you want, yeah, perfect.
Okay. So basically, I have to have the window already open before I start the sharing and make sure that it's there. So hopefully that'll be okay. And you can hear me fine.
Yes, yes.
Perfect. Okay. So we'll hope it works when the time comes. If I close the window, I guess it stops sharing, does it? See what happens. Or does it stay and remember what the last thing was? Stop sharing. All right. So I've got the controls here, so I just run them myself. And the microphone I just turned off. Okay, perfect.
Okay, perfect. Thank you, Mike. Colin, are you here? If you are here, please raise your hand. Thanks, Mike. Puyan,
Yes.
you want to play or play music, please?
Okay, okay.
Thank you. Okay. Hello, everybody. Hello, Dragan.
Hi.
Hi. So
You
you
can
have
hear me?
access to... Sorry?
You can hear me.
Yes, yes, yes. So you have your microphone, and I guess you have your video, and we are waiting for Colin.
Okay, and let's see. I need to be able to give microphone powers. Is that right?
Not really. If you just for questions, if you just say the name,
Yes.
we give. Yeah, we give.
Okay, we'll do.
Yeah. I mean, you have the access to give the microphone, but we can do it for you.
Yeah. That's. Thank you. Yeah, that'll be good. That'll be fine.
Yeah. So let's see if Colin is around.
He was here earlier.
He was, okay.
But not now.
I don't see his name, but if you're around, please raise your hand, and you're coming up in the list. I saw that Galen is here, so hi Galen, and we can check the system after the talks if you like. Okay.
I sent Colin an email just to see. Maybe he's in the wrong room or something.
Okay, thank you.
If Colin is not here, I wonder if we should make. Oh, there I see Colin. Okay.
Okay, so he's here. Hi, Colin. Yes. Do you see the microphone symbol on top right?
Yep.
Great. Hello.
Yeah, can you hear me now?
Yes.
We can hear you. Let's see if we can see your first slide.
Yeah, so you should go, Colin, on top right, besides the hand, there is one one icon, files.
Yep.
Okay, please click on that and you will find your presentation. No,
Oh, sorry.
this one is screen sharing, I guess.
Is screen sharing okay? Or should I do the file?
No. Do you want to show your file by screen sharing? Because we already have your file.
Oh, okay. All right, I'll just do that then. Yeah.
Okay, so if you click on the files.
And then I hit play?
Yes.
All right.
Okay, cool.
And you can have, both of you can have videos. So I turn off my microphone.
Cool. Well, welcome everyone to the afternoon session. Thank you, organizers. I don't know about the rest of you, but I feel more relaxed and a little better after that setup performance that we saw on video just minutes ago. So that was very nice. It's a controversies conference and tensions, and we did hear a lot of controversial statements over the past 2-3 days. Let us continue tonight. First, we have Colin Hill for the next half an hour, followed by 10 minutes questions. Then we'll have Mike Hudson. Colin is at Columbia University. Colin, off to you.
All right, thanks, Dragan. Okay, so first, thanks to the organizers for the invitation. This has been quite an interesting conference so far. So I'm going to talk about a few different things that broadly fall into this topic of exploring cosmological concordance, mostly with CMB datasets. And this is work done with a variety of people who are listed here, who I'll try to highlight throughout the talk. Okay. All right, so I just want to start off with a quick summary plot. So I've been trying to keep this compilation of different H0 measurements updated for the past few months. This originally started with a Twitter post, which I linked down here. So I'm not going to go through all of these in detail, but I'm kind of trying to divide things here into the two different main categories of H0 measurements. Measurements that assume a cosmological model, what I might call indirect measurements, and then direct measurements that don't assume a cosmological model. The main thing I want to emphasize is that I think if one looks at the very latest measurements with these different techniques, it's not maybe so clear that there's a huge problem for us to solve. I agree that there's definitely still hints of a problem, but the latest measurements from shoes, which we heard about on Monday, as well as the update to the gravitational lensing measurements from TD Cosmo, have kind of changed the picture a little bit for me. So I just think this is something worth keeping in mind. Okay, so quick outline. First, I'm going to review our results from the Atacama Cosmology Telescope, discuss their concordance with other probes. Then I'm going to talk about some ongoing work, which is going to appear very shortly on the archive, where we're looking at potential future biases on H0 that could arise in CMB measurements. Not problems in current data, but what could be a problem in future data. And then I'll talk about early dark energy. All right, so I'm going to start off with ACT. I'm mostly going to talk about results from these two papers, Iola et al. And Choi et al., which you can find on the archive and now published in JCAP. All right, so ACT is a wide area multi-frequency CMB experiment. We're located in the Atacama Desert in Chile, which, as you can see in this picture, is a great place to observe the CMB. We've been observing for the better part of 15 years now, with some gaps in there for upgrades to the detectors. So this is actually a picture of ACT itself, which is inside of that structure that you see. So that's a ground screen surrounding the telescope, but there's the telescope inside. ACT is a collaboration with, I want to say around 80 people now. This is our last in-person meeting in Princeton a couple of years ago now. So I'm just going to highlight these two main cosmology papers today from our fourth data release, DR4, which came out last year. But there's a wide variety of additional science that if you're interested, and I encourage you to check out, including gravitational lensing maps, component separated CMB and Compton Y maps, as well as our newest products, these DR5 maps, which are wider area combinations of data from ACT and Planck. And these are all on the Lambda server. This is not the focus of my talk, but as Yacine alluded to earlier, I'm an aficionado of the Compton Y thermal SZ signal. And these are some maps that I was intimately involved in the construction of, which show the gas pressure as traced by the thermal LZ effect constructed from ACT and Planck data combined, covering about 2,100 square degrees. So these are the highest resolution Compton-Y maps to date, although there actually are now just very recently some SPT-Y maps as well. All right, so I want to focus on our cosmology results. For this, we focused on the deepest 5,400 square degrees of the ACT data. So we covered actually about 17,000 square degrees with the survey so far, but some regions are much deeper than others in the sense that they've been integrated longer and so they have lower noise levels. So the power spectrum analysis that I'm going to show you includes the data from the deepest 5,400 square degrees. All right, so just to give you a flavor of what the data looks like. So this is the Planck data at 143 gigahertz in a patch covering about 600 square degrees. If you then include the ACT data in a relatively optimal fashion, which was done by Sigurd Ness in this paper, you can see that the fidelity on small scales improves dramatically. So if I flip back and forth, hopefully you can see that the image is really sharpened up on small scales. And in particular, we can also pick out small scale signals that are not resolved by Planck, like radio and infrared point sources, which you see as positive red spots in this map, as well as thermal LZ clusters that you see as blue spots. And using the multi-frequency data, we can make maps of the thermal LZ signal like I showed you a minute ago. All right, so skipping over years of very hard work by many people in the collaboration, these are our data release for foreground marginalized CB power spectra. So we have the TT spectrum up here, EE, a moderate detection of the lensing B modes here, and then the TE correlation down here. One thing I'll note is that due to the atmosphere and ground pickup and other issues, we don't get the lowest modes in temperature. So it is important to combine, for example, with WMAP or with Planck to cover the largest modes in the temperature field. All right, folding in the data from other current surveys, we have this very beautiful picture that's emerged, I think, of the early universe. So Planck is shown here, ACT, SPT pole, polar bear, and bicep 2, Keck, which is down here. I think this is a pretty amazing achievement for the field. And as I'll mention at the end of my talk, we're really trying to push ahead and do this even better in the next few years, really pushing out in the polarization field to get these high L modes in EE. Okay, so maybe the most important thing here is to think of ACT as a completely independent check of the WMAP and Planck results. There's no shared instrumental systematics amongst these three surveys. What you can see in our two-dimensional posteriors here, where ACT is in blue, Planck in purple, and WMAP in yellow, is that things look pretty good. Lambda CDM is a good fit to the ACT data. Within this Lambda CDM parameter space, we're consistent at roughly the 2 to 2.5 sigma level with WMAP and Planck, which statistically is fine. We can then combine ACT and WMAP to form a data set that has statistical power that's almost approaching that of Planck. It's not as precise as Planck, but we are getting close. And again, it's independent of Planck. So that's what's done here. ACT plus WMAP is shown in purple, Planck in light blue, and then ACT plus Planck in dark blue, where one has to be a little bit careful in the way you combine those to make sure that you don't double count data. So the main takeaway here is that ACT plus WMAP is in excellent agreement with Planck. We're mostly focused on H0 today, so I'm just going to zoom in on the H0 posterior down here. And you can see that the purple curve from ACT plus WMAP lies very nicely in agreement with Planck. Numerically, these are our results down here. ACT plus WMAP yields 67.6 plus minus 1.1. As you imagine, we tested these results against a huge range of variations in the analysis. I'm not going to go through all these in detail, but suffice to say that the H0 results are remarkably stable across a very wide range of changes in the analysis. So then putting this in context, this is a whisker plot that shows our latest ACT results in yellow, pre-ACT results down here in blue, including Planck 2018, and then just two of the recent local, well now three actually, I've updated this with a third measurement, three of the local H0 measurements. So this is the latest resettle measurement that we heard about on Monday, which has come down a bit from the previous 2019 measurement. So in terms of the tension, using this latest 2021 shoes measurement, it's about 3.3 sigma between ACT plus WMAP here and this shoes 2021. And as as we heard from Wendy Friedman on Monday, the tension with the TRGB results is much lower. In fact, they're statistically consistent. All right, so that's the context currently from ACT. The main takeaway there is that ACT yields results that are concordant with those of Planck with a completely independent data set. As we look ahead to the future of CMB measurements, I've been thinking hard about whether there are subtle issues we might need to think about that could affect our inference, for example, of H0 or other parameters from upcoming CMB data. And in recent work that's shortly going to appear in the archive with Fiona McCarthy and Matthew Montevichero from Perimeter Institute, we've been looking at interesting effects that arise due to nonlinear CMB lensing in the CMB power spectrum. So I'm going to talk about this. This is all work that's, I guess, preliminary, but it'll be on the archive very shortly. Okay, so just to review the physics here. So gravitational lensing of the CMB is a very important effect on the primary CMB power spectra, and it becomes important as you go to small scales or high L. So this is the TT power spectrum, the EE power spectrum, and the TE power spectrum. TE is plotted on this funny SimLog style where you can plot log scales with positive and negative values. And then down here in the right corner is the ratio of the lensed to the unlensed power spectra for each of those observables. And what you should take away here is that as you go up beyond L of say 3,000, 4,000, lensing becomes an order unity effect. It becomes the dominant contribution to the total observed power, which means that you're going to need to model this quite precisely. In comparison here, I'm showing the noise curves that I've computed for the Simons Observatory in green and CMBS4 in red. These actually fold in Planck data as well, which is why they have good properties at low L. And what you can see is we're measuring single dominated modes out to L of 3,500 in temperature, and probably L of 3,000 in EE with CMBS4. So we're really getting very sensitive to CMB lensing. Now, CMB lensing is nice because it's mostly a linear observable, but as you probe this at higher precision, you do have to start to worry about nonlinear evolution and baryonic effects, which can alter the matter power spectrum and thereby alter the CMB lensing power spectrum. So by baryonic effects here, I mean things like feedback from AGN, feedback from supernovae, cooling processes, things like that. So what I'm showing here is the ratio of, in the top left here, the CMB lensing power spectrum in a calculation including baryonic effects versus that in a nonlinear dark matter only calculation. So the denominator here is, for example, the usual halo fit fitting function, which is a dark matter only fitting function, but it includes nonlinear effects. And the different curves correspond to different baryonic implementations from different hydro simulations, like Illustrious TNG, Bahamas, Horizon AGN, or the OWLS simulations. And you can see generically they all predict a suppression in the lensing power spectrum. And this happens from AGN feedback, basically ejecting gas from halos. Now, if you then propagate these lensing power spectra into the primary CMB power spectra, that will have an impact at high L for the reasons I just showed you on the previous slide. So here in the other panels, I'm showing the ratio of CLTT, CLEE, or CLTE in one of these baryonic physics models versus a dark matter only calculation. And you can see that out at L of a few thousand, you're getting changes on the order of a few percent. And although that sounds small, our data in these upcoming surveys is going to be so precise that these effects, in fact, actually matter. Okay, so what's currently been done in primary CMB analyses to date is what I might call set it and forget it, where it refers to the default halo fit or HM code modules in CAM or class, which are the Boltzmann codes that we use to model cosmological observables. So these are fitting functions, which are tested against n-body simulations, and certainly get the dark matter, we think, quite accurate. But as I've mentioned, there's these baryonic effects that will need to be taken into account. So this set it and forget it approach, as I'll show you in a second, does not suffice for Simons Observatory or CMBS4. So to look at this, what we've done is to take the noise properties of these surveys. So here I'm showing you for CMBS4, and look at the bias on cosmological parameters that you would get if you analyzed your CMB power spectrum data, assuming that halo fit was the correct model, but in fact, the true signal was generated with, in particular, in this case, the OWLS AGN baryonic feedback model. So this plot shows the fractional bias in units of sigmas on different cosmological parameters as a function of the maximum multipole that's included in your analysis. And what you can see is that for CMBS4, for which we could certainly get out to Lmax of 5,000, you're getting a significant bias greater than 1 sigma on some of these parameters. And this is coming from a mismatch, again, between your model of the CMB lensing field and what the actual true CMB lensing field looks like. So for CMBS4, the bias can be on the order of a couple sigma on H0, over 1 sigma on N effective, which tells us that we are going to have to think about how to solve this for these surveys. I do want to emphasize that this is not a problem for Planck, which has Lmax of 2000, so you can see all the biases are way below a sigma, or even for current ACT and SPT data, which is somewhere in the regime of Lmax of maybe 3000 or so. But for SO and S4, this is important. So we've thought about ways to mitigate this. The easiest and crudest way is to just throw away all of your TT power spectrum data at high L. Obviously, you pay a small penalty in the parameter error bars because you're throwing away data. But it turns out that the biases are dominated by TT. And that's because you have more signal-dominated modes in TT. And also the effect of lensing at high L in a fractional sense is larger in TT than it is in EE or TE. And that's because the gradient in temperature is larger. So that would work. Another option is to introduce parameters that describe these baryonic effects. So in the HM code module, there's actually 2 parameters one can introduce that characterize baryonic effects. And you can then marginalize over those in your primary CMB power spectrum analysis, which is a sort of a funny thing to think about doing. But it turns out that this works. So this is a similar plot to what I showed you before. But you can see the scale of this y-axis, which is showing these biases, is way below 1 sigma now. So these are fractions of a sigma. So as long as you marginalize over some sort of model for the baryonic effects, it should suffice. And then the third method that one could think about doing, which is very data-driven, is to actually de-lens your temperature and E-mode maps using your knowledge of the reconstructed kappa map from the higher order statistics. Or you could use external tracers of kappa like the CIB or galaxy surveys. I like this approach because it's robust and data-driven, so you're not assuming some model. And it was actually shown that de-lensing like this could actually improve constraints on parameters by reducing covariances. But I think it's unclear if this will work on the very small scales that we're interested in here, right? We're talking about L's of order a few thousand, whereas de-lensing so far has mostly investigated how well it'll work at lower L's. So I think further work is needed. But I think all these 3 approaches are promising. So we know what to do to solve this problem, but it is a new effect that will need to be taken into account in upcoming analyses. The last comment that I want to make on this topic, or related to this topic, is actually about the accuracy settings in Boltzmann codes. So while we were investigating this, one thing that we learned was that the precision of the lensing calculation in CAM or class actually will need to be improved for the analysis of upcoming CMB datasets. It's easy to fix. You just have to turn up the precision parameters in these codes. But the default values in the codes, although they suffice for current data, are not accurate enough for SO or CMBS4. So there's a similar type of plot to what I showed you before, fractional bias versus Lmax, where now instead of the mismatch coming from a baryonic model versus a dark matter only model, the mismatch now is from default accuracy versus the true high accuracy. And then you can see the fractional biases here get to the order of several sigma. So that would be a major problem. But this is easy to fix. You just have to run CAM or class with the precision parameters turned up higher. And I'll note that even for current data, actually from ACT and SPT, one thing that we've learned very recently is that if you want to do a precise chi-squared comparison of the best fit lambda CDM model to best fit extended model, for example, the EDE model I'll talk about in a second, you actually need to use increased accuracy settings for that as well. So it does have some relevance. The posteriors are pretty much insensitive, but the best fit chi-squared comparison does have some sensitivity to this. Okay, so now in the, I guess, final 10 or 15 minutes, I want to talk about early dark energy and cosmological concordance. This is work in 2 different papers that came out last year with this group of people, Evan McDonough, Michael Toomey, and Stefan Alexander from Brown, Misha Ivanov at NYU, Markus Simonovic at CERN, and Matthias Zaldarjaga at the IAS. So a brief review of this early dark energy model. The motivation here, as most people probably know, is to resolve the H0 tension. And how does this work? So what we're looking at here are posteriors on H0 inferred from lambda CDM, fit to Planck plus shoes plus some other data, including BAO, for example. And then the red is the EDE model fit to those data sets. And you see that H0 shifts upward if you fit the data in the context of this EDE model. So how does that work? As we've heard a little bit already, the idea is that you want to decrease the physical size of the sound horizon that's imprinted in the CMB. So the sound horizon is given by this integral of the sound speed, Cs, dz over h of z, integrated from the beginning of the universe to the time of recombination. Now, in lambda CDM, the only quantities that enter that calculation are the physical densities of baryons, dark matter, and photons. And as we'll see in EDE, there's additional parameters that enter the calculation. Importantly, what we actually measure in the data is the angular size of the sound horizon, which goes roughly like the inverse of the peak spacing in the power spectrum. Now, if you hold theta s star fixed, because that's what we measure, then by decreasing rs star, you would decrease the inferred angular diameter distance and then increase the inferred h naught. So that's the mechanism for how this approach increases h naught, inferred from the CMB. All right, in EDE, as I mentioned, there's additional parameters that will then affect the sound horizon. That's the crucial idea. And there's a variety of other models that also have this general sort of motivation. So how do we implement this in a fundamental physics sense? So the generic approach has been to introduce a new scalar field, really a pseudo-scalar field with a well-designed potential. So you design it such that the field is initially frozen on its potential due to Hubble friction. So this is the Klein-Gordon equation in an expanding universe. And so initially it's frozen by the friction term here, the phi dot term. So it's acting as dark energy with equation of state W equals -1. Now, as the Hubble parameter decreases, eventually when it becomes of order of the field's mass, the field will start to roll, and then it will oscillate around the bottom of its potential. And you can put in the numbers and figure out what this implies about the mass of the field. It has to be around 10 to the -27 electron volts. So it's a very light field, which kind of motivates why people think about axion-like particles here. And the oscillatory solution can be written down easily for simple potentials, although for more complicated ones, like we use in the actual analysis, that has to be done numerically. Let's see. So the key components of the model, I've already mentioned these ones. The other important one is that at late times, we need W to be greater than 0, the W of this, the equation of state of this new component. So that way its energy density contribution will decay away faster than that of matter. We don't want this thing hanging around at late times and messing up the rest of cosmology. So the canonical potentials that have been shown to work pretty well look like this. You have basically an axion like 1 minus cosine of phi type potential taken to some exponent n. And I think these are motivated from appeals to instantons and string theory and things like that. But it's sort of just a phenomenological construction, I would say. So n equals 2 or n equals 3 both give you the type of behavior for the late time equation of state that is needed, that I mentioned up here. N equals 3 seems to work best, so we basically just leave that fixed. The data aren't really sensitive to whether you choose n equals 2, 3, or some fractional number, but the higher the value of n, the more terms you're tuning in this potential. If you think about the potential as some Taylor series, then even n equals 3, right, we're already tuning multiple terms in that Taylor series. Okay, so in terms of how we actually parameterize this for the analysis of data, the conventional way to look at this is to look at the fractional contribution of the early dark energy to the total cosmic energy budget as a function of redshift, which is what I'm showing you here. So initially it's irrelevant. It's just sitting there as another contribution to the cosmological constant. And then it becomes dynamically important, say around matter radiation equality or so. And then as it starts to roll, then it rapidly starts to fade away, and you can see the oscillations that also develop. So the parameters that are used are FEDE, which is the maximal contribution that the field ever makes to the total cosmic energy budget, which occurs at a redshift ZC, this critical redshift, which is closely related to the time when the redshift when the field starts to roll. So those are two of the parameters, and then the third parameter is just the initial field displacement on its potential, which turns out needs to be relatively near theta equals pi, actually, from the data. One thing to keep in mind is that these effective phenomenological parameters have a highly nonlinear relation to the physical parameters in the scalar field potential, for example. And if you do the analysis in terms of those physical parameters, the results actually differ a bit because the implicit priors are different. So that's one thing to keep in mind. Okay, so the model is interesting because it maintains a good fit to CMB power spectrum data while having a higher H naught. So here I'm showing the TT power spectrum for two different models, lambda CDM in black and then EDE in dash red, where the EDE model has a significantly higher H0. And the fractional difference on the right, you can see that it's within roughly 1% or less out to Lmax of 2000, roughly when the Planck data runs out of steam. And the physics here is exactly what I told you a minute ago. It's due to the decrease in the sound horizon. Now, what hadn't been looked at prior to our work in much detail was the change to the matter power spectrum in this model. So we wrote a modified version of the class Boltzmann code called class EDE, which you could download, and we have many example notebooks to make it easy to use. And we looked at how PFK changes. So these are for the exact same models that I showed you in the previous slide. So in contrast to the indistinguishability of the TT power spectrum, here you can easily see, even on a log plot, that there are differences. And if you look at the ratio of the EDE PFK to lambda CDM, you can see that there are differences on the order of 5 to 10% over a range of wave number that's well measured in current data, for example, from DES, which suggests that large-scale structure data should have something interesting to say about these models. The reason that these PFKs differ is not really related to EDE, although there are some interesting physical effects there, which we could talk about later if people are interested. The main effects are really due to the shifts in the standard cosmological parameters that are required to fit the CMB data in this model. So the biggest change is that the cold dark matter density, omega CDM, goes up significantly, and that's because you have to compensate for the early ISW that's associated with this EDE field. It's trying to suppress the growth of perturbations, so you have to include more dark matter to compensate. In addition, there's a scale dependence to this suppression, so you end up having to increase NS a bit in order to compensate for that. And the upshot is that the late time parameters, in particular sigma 8, get increased as a result of these changes. So S8, which is the best constraint parameter from weak lensing data, as we've heard, goes up by quite a bit in this model. So we sought out to try to evaluate the concordance or not of this model using a variety of cosmological data sets, and I'll just summarize a few of the results here. So first, we set out to look for EDE in the primary CMB alone, which hadn't actually been done previously. So we looked at Planck 2018, just the primary CMB data. So the posteriors are shown here, and obviously you can't quite look at these in detail, but what we should notice is that the EDE ones, which are in blue, are pretty much consistent with the lambda CDM ones in red. So you don't see any big shifts in the parameters when you look at Planck alone. There's a broadening of error bars, of course, because there's more parameters in this EDE model, but there's no big shifts. In particular, the H0 tension persists. One can look at this in terms of the constraints on the actual EDE parameters themselves. And the most important one is this amplitude FEDE, how much of this early dark energy is there. And Planck doesn't prefer any non-zero amount of this. You just get an upper bound of about 9% at 95% confidence. So then fast forwarding through a bunch of analyses, this is then our global analysis. We're fitting basically all cosmological data sets except for shoes. So we're trying to ask the question, what do the indirect cosmological inference say in this model? So we can compare that H0 to what you get from the direct model-independent local measurements. And importantly, we're including data from weak lensing surveys that was not included previously. So again, what you see here, looking at EDE in blue and lambda CDM in red, is that there are not big shifts that are seen. There is a small upward change in H0, which I've zoomed in on here, but there's not a major shift to bring it up into concordance with the local measurements. And the reason that this happens is that, as I mentioned, omega CDM needs to go up in order to fit the CMB data with this early dark energy, but that increases sigma 8, and the large scale structure data does not want to let you increase sigma 8. So you're put into a rock and a hard place, basically, and you can't get a big shift. We can look at this then again in terms of the EDE parameters themselves. So here what's being shown is in blue, what I just showed you a minute ago. So that's all the data sets without shoes. And then if you actually include shoes, this is shoes 2019. In red, it's in tension, so it's really not a sort of valid thing to do, I think, to include it. But if you do, you get an upward shift in the EDE fraction, but it is still consistent with 0 within a couple sigma. So if in the global analysis without shoes, you get an upper bound of 6% on the FEDE fraction. And the main thing to take away, if you don't remember anything else, is that if you compare shoes to this indirect inference, even in this early dark energy model, it's still in 3.3 sigma tension. So there's no real hint of cosmological concordance being restored. We actually sought to then improve these constraints further by folding in this very, I would say, powerful likelihood that's been developed using the effective field theory of large-scale structure for the BOSS galaxy power spectrum data. Fast forwarding through a lot of interesting stuff that we worked on to make this happen. But here are the main results when you do that. So Planck alone here is in green for EDE. Those are the ones I've showed you before. Blue is the EDE analysis of Planck plus this EFT BOSS likelihood plus the S8 data from DES, HSC, and KIDS. And then red is lambda CDM fit to those data sets. And again, we don't see any big shifts. We just get tighter and tighter upper bounds on this amount of early dark energy, where it's now constrained to be less than about 5% at 95% confidence. And the tension of H0 with shoes is about 3.5 sigma, even in this early dark energy model. Let me skip this in the interest of time. The takeaway here is just, where does the constraining power come from in this EFT likelihood? And it turns out it's in the cold dark matter density, which had been shown previously in work from Misha Ivanov and collaborators. I just want to address quickly, there's been some statements in the literature suggesting that the constraints that we're seeing are driven by so-called prior volume effects, where the idea here is that as you approach the FEDE equals 0 limit, that these other two parameters, ZC and theta I, become degenerate. So there's a larger prior volume at FED equals 0. In my opinion, this is actually just a way of Bayesian inference imposing Occam's razor in some sense. But one can actually assess these effects quantitatively by using what I would think of as more frequentist-based methodology. So we've done this. You can find lots of details in the appendix of this paper, Ivanov et al., where what I'm showing you here in solid is the marginalized constraint on FEDE coming from either, let's see, in red, the BOSS plus Planck analysis, or in blue, BOSS plus Planck plus the S8 data. And then the solid line, sorry, the thin line rather, is the best fit log likelihood profile, where what you're doing is that each value of FEDE, you find the best fit value of all the other parameters. So this is saying, can I find some tuned value of all the other parameters at a given FEDE value, which could fit the data? So the first thing to take away is that the overall best fit point here is at a very low value of FEDE. It improves the fit over a lambda CDM by about delta chi squared of 4, which is not surprising because there's 3 additional parameters. So that's very much just consistent with fluctuation you get with introducing additional parameters. If you look at the curves that include S8, then the Hubble tension resolving value of FEDE, which is about 10%, is significantly disfavored, and the two approaches agree very precisely. In the case where you don't include the S8 data, there is some tuned value that you can find for the other parameters that would let you get a model that would resolve the H0 tension with comparable chi-squared to lambda CDM. But one might want to ask then, is there some look elsewhere effect? In other words, how specially tuned do I have to make my parameters to find that point? And so you can look at that by looking at the so-called mean likelihood profile, where now you're averaging the log likelihood over all the other parameters in the model at each FED value, rather than finding the best fit. And if you do that, then you find that there's very similar behavior between that mean likelihood curve and the usual Bayesian marginalized posterior. Here I'm showing the result for just BOSS plus Planck, where you see that there's nice agreement. If we included the S8 data, this would peak even more sharply at FED equals 0. And I should emphasize, this is the same method that's used by the Planck collaboration to assess these prior volume effects. So the overall conclusion is that the prior volume effects, if they're driving anything, it's much less than 1 sigma of the total constraining power. I think I'm pretty much out of time, so let me skip this.
Yeah, if you could wrap up.
I'll wrap up very shortly. I just want to emphasize that after our work came out, there was a very nice paper from Jadamzik, Pogosian, and Zhao. I think Levon might talk about this tomorrow, where they basically generalized some of our conclusions to other sound horizon reducing models. So let me leave that out. The main summary then from this EDE section is that we don't see any evidence for this early dark energy component in analyses of cosmological data from the CMB or CMB plus large scale structure. The direct measurements from shoes, in fact, are still in tension, and even in this model. And the basic physics of why this happens is what I told you earlier. So from the theory perspective, one might want to think about it, ways that you could tweak this scenario to get around some of these constraints. We've been thinking about that recently with Evan and with Wayne Hu and others in Chicago. I'm out of time, so I'm not going to show you the outlook. I just want to emphasize that we are going to continue making very precise CMB measurements in the very near future. Our constraints on H0 are going to improve even further to 0.5 km per second or megaparsec from the next ACT release. and then up to about 0.3 kilometers per second per megaparsec in the SO analysis, which will follow later this decade. So let me stop here, and I'm happy to take questions. Thanks.
Thank you, Colin. Thank you. Super nice, super bright future there with future surveys. For questions, either raise your hand or type them in the chat and I'll read them out. For the moment, Adam has his hand up. Adam, go ahead with your question.
Hi, Colin. That was a very nice talk. A lot to unpack. I really look forward to those future measurements. I've seen some back and forth, I know, about the EDD papers with the Vivian Poulin, Tristan Smith, and Kay Minkowski. The question actually I wanted to ask you, in Eleonora's talk, she went through this sort of every combination of 2 H0 measurements you could throw out, and the lowest she was able to get the tension that way was down to about 3.5 sigma. If you pick just the right 2 to throw out. I looked at you had quickly put up this H0 diagram, but I looked it up on Twitter, and it looks to me like you're removing 5 of them or something like that, or not including 5 of them. The latest HST surface brightness fluctuation measurements, the type 2 supernova results, the latest Gaia calibration, the Maser Cosmology project, and you're using just one of the TD lens variants. And I guess my question is, I mean, as we struggle to figure out what's going on, do you think, is that a valid approach to throw out so many different measures?
Right. So I don't think I threw out anything, actually. So all the ones that you just mentioned are actually on the plot. As far as I know, I actually updated it a couple of days ago with your latest measurements from the Gaia calibration.
Well, I don't think you had the Blakesley surface brightness fluctuations from HST.
There is an SPF point on the
yeah,
plot.
but
being updated with everything, but maybe not every single thing. I want to mention that I didn't take any averages of any of the measurements in anything I quoted, because as I noted on the slide, very few of these are actually completely independent measurements. So I think Eleonora is taking averages of many things that are highly correlated, which isn't really statistically correct. So yeah, I didn't ever try to quote averages of different measurements.
Okay, and it still looked like you were choosing a value in between, like a sort of in between value, like, to the right of the early universe, to the left of the local ones. And I mean, if one is trying to figure out what is the true value of the Hubble constant, and somebody puts a gun to your head, I can understand doing that approach. Right. But I think that sort of would lose perhaps the chance to see what causes the difference.
Oh, I completely agree. Yeah, I think it's very fun, as you can tell from the rest of my talk. It's very fun to think about how to solve this problem. I think I take a somewhat more conservative viewpoint on what the data is currently telling us. And for me, this just motivates that we need to get out and keep measuring things as precisely as we can. And,
sure, I totally agree with that.
Yeah. Dragon, I think you're muted if you're talking.
Sorry. Yes, there are more questions in some, I think first Ali Akbar, then Wendy.
Hi, Colin. Thank you for the very nice talk. I have a very crazy question and comment. Is it possible to unite the idea of the EDE with fuzzy dark matter? Is it possible? In principle, the fuzzy dark matter is nothing but a light scale. The EDE idea is more or less the same. Is it possible to unite the ideas? It may help to solve the problem with sigma 8 and omega DM or so, because both of them are the same, at the same time can solve play the role of the dark energy, early dark energy, and dark matter. And
that's an interesting point. It is true that the qualitative type of potentials, right, are kind of similar. One problem is that the mass scale involved is quite different. So for this early dark energy field, you're looking at something that has a characteristic mass scale of order 10 to the minus 27 electron volts or so, whereas for the fuzzy dark matter, it has to be on the order of 10 to the minus 22 electron volts. So it's possible that you could design some sort of model where these things are connected somehow, but intrinsically the scales involved are quite a bit different.
Yeah.
Thank you.
Think about this idea?
It's not something I'm currently thinking about in detail. We are thinking about some other ways of extending the early dark energy model, which we should have some results out pretty soon on the archive.
Thanks.
Thank you. Wendy. Let's see if I can unmute you. Maybe not. Okay, we should hear you now.
Okay, yeah, just a short comment. I just wanted to follow up on Colin and Adam's discussion, and I think everybody has the right attitude now, which is let's be conservative, let's look at the systematic errors, but just in support of what Colin just said, not all of the measures right now are independent, and just behooves us to remember that. And Adam and I have a friendly disagreement over that, and I think the results now are intriguing, but that we do have, it behooves us to look further into the systematics. And so whether this is a 3, 4, 6 or a 2 sigma discrepancy, we'll be able to ascertain, I think, unambiguously in the next few years.
Yeah, I agree. Thanks.
Thank you, Wendy. Yeah, good point. I'd say let's go with 2 more questions. We first have Alex Hall and then Dick Bond. Alex, go ahead.
Thanks. So you include the lensing S8 constraints when you constrain the early dark energy models.
Mm-hmm.
But if the tension in S8 with Planck is not just a statistical fluctuation, then there must be the systematics or new physics there. So given that the EDE models don't resolve that tension, that means there still must be either systematics or new physics in there. So given that, how powerful is the fact that EDE makes the S8 tension worse? How powerful is that in telling us something about the model?
Yeah, I think it's very important, to be honest. It's really what drove our statement that this scenario doesn't restore cosmological concordance. There are others in the field who argue that we should just discard the data from DES and HSC and KIDS. That's really at the crux of our disagreement that you may have seen in the literature. I certainly don't subscribe to that viewpoint. I don't feel comfortable throwing away the work of hundreds of people. Yeah, it's telling us that some different approach is needed in order to restore concordance. It can make some small improvement in the H0 tension, reducing it from say 4-point-something sigma to 3-point-something sigma, but it exacerbates the S8 tension. So to me, that gives an indication that this scenario alone isn't really on the right track. And as I mentioned, this paper from Levon Bogosian and Carson Jadamczyk kind of generalized our conclusion about that to other scenarios that only reduce the sound horizon. So if you're trying to solve H0 by reducing the sound horizon, you're going to need some additional new physics or new dynamics to get around essentially this S8 problem, or to fit the BAO data correctly. You're kind of wedged between these 2 different things. But Levon will probably talk about that more tomorrow.
Last question, Dick Bond. You are muted for the moment. Let's see if Nima or somebody can unmute you.
He has access to the microphone, so he has.
So Dick, if you see a microphone sign top right of your screen of your browser.
No, I don't.
Let's wait another moment.
Dick said no microphone sign. Dick, you could just type your question if you want.
Okay, good to go. Can you hear me?
Yes, I can hear you.
Yeah, good job, Colin. Great sales pitch for our brilliant ACT results. That was all really good. I want to go back to the early dark energy story. So is N completely phenomenological, or is there justification for having that N of about 3 or something like that?
I would say it's completely phenomenological. Yeah, from my conversations with people who approach this from the fundamental physics perspective, string theorists and so on, most of them tell me that N equals 3 is a patently crazy value for this type of.
That's what I would have said myself.
Yeah, actually, Steve Weinberg told me that when I gave this talk at Texas. So
yeah. Okay. So and so what happens if it all completely crashes if you use N equals 1, say,
Yeah, n equals 1 doesn't work at all, because the problem is that at late times, the equation of state of this new component is W equals 0. So it acts like another contribution to cold dark matter, and it just messes up everything, basically.
Okay. And it's basically associated with the rate of the fall.
Yeah, it has to do with the shape of the potential, right? So as
Yeah.
n goes to a higher
No, I
value, you get
understand.
steeper and steeper, and then flatter and flatter and out near the bottom. Yeah.
Yeah, I'm thinking about a little bit of coupling of the dark energy. And there is this well-known effect that if it's coupling to trace T, stress energy tensor, that in the extremely relativistic dominated regime, you basically have a pinned field. And then as you go through equality, it'll get released. And an interesting question is whether, instead of it being the ordinary potential, there is some kind of effective curving up associated with that effect that might accelerate things, that would have nothing to do with invoking instanton physics, which is what you're basically doing now to get the potential.
Yeah, so far that's what's been done. Yeah, that's an interesting idea. I mean, it might be possible through some argument like that to connect this, as well to resolve the coincidence problem, where one has to try to explain why this field becomes important around matter radiation equality.
Yeah, and so just one other quick comment. I showed a few results in my talk yesterday. A graduate student that Renee Hlozek and I share, Alex Legue, is looking into the fuzzy scenario, but in a mixed fuzzy dark matter plus CDM. And we're looking at allowed values for that in the current universe. And you know, the figures are going out to basically 10 to the minus 31. In other words, there's this interesting collision. I think somebody raised that question. There is this really interesting collision of the fuzzy scenario potentially with having an impact at the recombination era. Not clear, but it's a fun other way to look at the system, which you're already doing by invoking the axion potential.
Yeah,
the
with a higher value of n.
Thank you. Very interesting. Thank you, Dick, and thank you, Colin. I think in the interest of time, let's get going. We are slightly over. Thank you, Colin, again. Maybe I think you have to quit sharing your screen now, and let's move in Mike Hudson. Okay, Mike, I can see you. Let's see if we can see your slides. All right, Mike Hudson. Yes, we can see them. University of Waterloo. Mike Hudson, he'll tell us about cosmic flows. Mike, off to you.
Thank the organizers for inviting me. It's a pleasure to be here, even though it's only virtual. So I'm going to try to tell you the story of cosmic flows, how they play into this. And I thought that I'd start with a cartoon that Sabir Sarkar showed yesterday when discussing related matters from George Smoot's Nobel lecture. So this shows the velocity components of the CMB dipole as observed from the sun, and it basically breaks it down. There's an Earth around Sun component, the motion around the galaxy.
Mike, I'm hearing you interrupted. I don't know if that's the case for others. So I wonder if you don't share your picture, that's going to be better.
Okay. The connection got choppy. I don't know why. I'll try to turn off my video, maybe.
Yeah.
So we know about all these motions. They're pretty motion local group and written toward the great fractal. It's a slightly outdated notion that I'll come back to. But what's shown here schematically, there's objects around which are responsible for the motion with respect to the CMB. So this is what this talk is going to be about, and I'll show how you can measure these and how you can predict these peculiar velocities. So measuring them first, at low redshift, the peculiar velocity is just the redshift minus the distance times h naught. So how do we measure this? Measuring redshift is straightforward. Take a spectrum, transform it to the CMB frame if you like, then your peculiar velocity is C frame. The hard part of this is measuring the distances. I think we don't actually care the absolute distance in this case. We only care about the Hubble times the distance. In other words, the distance but in units of meters per second. And that's something you can do without an absolute distance scale. You can do it if you have sort of a reverse distance ladder that comes in from the outside. So the main methods for measuring A naught times R are ones that people are very familiar with now. The supernovae are very accurate but sparse. And older methods, such as the Tully-Fisher relation and the Venn relation, these methods are good about 20% in the product H naught R. What that means is what you have observationally is a set of sparse and noisy tracers of the velocity field. Because of the distance uncertainty, 20% for most indicators, is a multiplicative factor, it means that this method really works well at redshifts. Okay, the other ways of using peculiar velocities, which I'll just mention for context, are redshift space distortions, which many of you know about. That's a statistical method, it's cosmic variance limited. So you need enormous volumes to make this method work. The third method was an upcoming one, the kinetic Sunyaev-Zeldovich effect. Very weak signal in the CMB, but as the CMB data get better, I think the prospects of this are very exciting. So I'm going to focus on the first of these methods, that I call direct distance estimates. So that's the observation side. How does this work theoretically? Well, here I like to give a little bit of a background and use your intuition that you already know from accelerations due to gravity, right? So have a density field of some matter. Predict the acceleration just by integrating with 1/r² law. Peculiar velocities behave exactly like this, except you replace the density with the perturbed density and the fluctuation. So the peculiar velocity is proportional to the peculiar acceleration. So it looks like this. We now have delta appearing here. But other than that, it's a 1/r² law. Okay. It has this important parameter f in front. So before we leave this, remember that delta can be negative. So an underdense region can push, as well as an overdense region can pull. And of course, we know that the delta field, a Gaussian random field, is going to introduce contributions from structures on all scales, both positive and negative. So a picture of a number of attractors is too simplistic. In lambda CDM, you know what this f is. It's the logarithmic derivative of the growth rate. And that can be expressed as, in lambda CDM, as omega matter to the power 5. Okay, and notice that that exponent is very close to the 0.51 that used SA measurement, which we'll come back to. All right, so I'm going to tell you the story. Most of this work is by Santa Bua, former PhD student of mine that I shared with Gazelle Nizjadi. He's now a postdoc in Arizona. Long-term collaborator Guillaume Lavaux, and some new work by student Amber Hollander. So we want to apply this equation that I've already shown you. The problem is we don't know what the underlying delta of the mass is. Okay, so in this game, we're going to make an assumption that we can measure this through the fluctuation in the galaxies. And we're just going to assume linear biasing. Okay, so if we replace delta M with delta G over B, we get an B here. And that means we measure a degenerate combination of parameters, usually beta in the jargon. The other problem with trying to do this with a real survey of galaxies is that we don't have an integration out to infinity as one would like. There's usually a limit to the data extent. It's called our max. All right. So there's contributions outside of our max that no approximate the dipole. In other words, just a vector, the lowest order part of the field, and we call this residual bulk flow. This is not the motion of the entire volume, it's the contribution to the motion coming from outside the volume that we can map. So those are the two parameters that are measured, and they can both be fit directly from the data. So the name of the game is to take a map of the density field, plug into the equation, and predict the peculiar velocities, and compare them with the observed ones. So how does this relate to S8? Well, as follows. If I can measure this parameter beta, and do linear biasing, fluctuations in galaxies linearly relate to the fluctuation in mass. And those fluctuations in the galaxies I can measure directly from the data. So I can put together measurable quantities, both observable from the data. The bias factors cancel out, and I get left with F. Remember, F is omega matter to the 0.55. So that's, in a nutshell, the name of the game. Now you might ask, how well does this work? I've glossed over one thing. You go step. That in this delta G here that we can from the data, we put in the raw delta G, which would effectively be a set of delta functions. This is all based on linear perturbation theory. And so we want delta G in general not to be too large. So the solution kernel. Okay, so we can test how well this works in simulations. So in both simulations, it turns out it works extremely well. So this, on the vertical axis of this diagram, is essentially this is a measure of the bias. In other words, it's the recovered data if you perform this process on an in-body simulation with fully nonlinear velocities, and you compare it to a predicted peculiar velocity and try to recover the right values. So what it shows is that depending on which analytic model you use, values are unbiased at the level of just a few percent, 2 or 3%. If you smooth at the magic smooth scale or measure, you get biased either way. So that's something you can calibrate directly from simulations. And it gives a hand on how accurate it should be. So when you smooth at that smoothing scales, you get unbiased predictions. There's still a residual, which we model as thermal scatter, but it's small. It's about 150 kilometers per second. So most of the motion is well described by this simple linear theory with some smoothing. Let's get the data. This is a survey we call 2S. It's a combination of the 2 mass redshift survey, slow sky survey, which doesn't cover the whole sky, and 60F survey in the south, which covers most of the southern sky. It was published in a previous paper by a student of mine, John Carrick. So this is a slice through the supergalactic plane, the plane that contains many of the important structures. And it's a smooth density field where the density shown here in the bar. We live in the center of the plane. 0, 0 is coordinates, a little star in the local group. Okay, and we see that they're structural around us, and it's this integral that we have to do over this field to generate the predicted peculiar velocities. So here are structures labeled. This here is Virgo, close to us. Subi said there are no evidence for the great attractor. But here's the great attractor. More distant great attractor.
Hey, Mike, can I interrupt you?
Yeah. Yes.
The voice was barely possible, but it's not barely possible anymore. People who know here are suggesting you try to log out and reconnect. Can you try that?
Okay, I can try that.
That's the advice they're giving, and let's try that because it's now. It was a little bit like Stephen Hawking voice, which is it worked, but now not anymore. So let's try that.
I'm not sure why. I'm right next to my Wi-Fi router, so it should be okay, but it obviously isn't.
Who knows?
So let me try. Take a few seconds.
Yes, no problem.
Okay, I'm back. Does that sound any different?
For the moment, it does. Yes. Slides. Let's see.
I was sharing again.
Okay, good. Because there is another possibility. If you want, you can use your files on our system.
Do you think it's the sharing? I don't know if it's the sharing or something else.
Okay, let's go ahead and share. Okay.
Let me know if it gets bad again. So these are some of the structures in the nearby universe. And this object here, called labeled GA, the great track, was last when exists as over density.
It's not fine again, unfortunately. Let's try the slides option.
Okay.
So yes, okay, good. So Mike, there is an icon files besides the hand.
Mm-hmm.
And then if you click on that, you can find your file there and then choose that one and then play, please. Yes. Then you can go, yeah.
Okay.
Thank you.
Okay, I'll try it in this mode. Hopefully that'll be better.
Sounds good. So let's get started.
So my point is there is a great attractor. There are many structures. It's a complicated Gaussian random field and you have to integrate over everything. For those of you who are bored of this talk, that you can go follow this, you can hold up your phone and follow this QR code or go to this URL and you can play around with this distribution in 3D. Since this is now a PDF, I can't show you the little animation. You'll have to do it yourself. But it does show you all the structures, and it shows you that many things, you know, although there is a supergalactic plane, it's not so dominant. So there's structures out of the plane as well. So let's show an example of how this works in practice. We take a data set. Okay, so it could be For example, SFI is a Tully-Fisher data set. 2MTF is another Tully-Fisher data set. Second amendment is what we call a set of supernovae. All right, that goes on the left-hand side. And then we take this 2M++ data field that I just showed you, put it on the right-hand side, integrate it, and fit for these two parameters, beta and V external. It's maybe a little bit hard to see the details here, but essentially what this shows you is the comparison between the unscaled predictions on the x-axis. When I say unscaled, I mean with a beta equal to 1, okay, versus the observed velocities on the y-axis. Now, the individual measurements are very noisy, so we've binned them, and that's shown in the blue. And they're different data sets. The top panel shows supernovae, and then we have Tully-Fisher galaxies in the bottom 3 panels. Right? And the important point here is that all of these comparisons show a slope. The slope is the fitted value of beta that is highly significantly different from 0. Okay, and the values of beta themselves are consistent with each other. So you can then do the exercise that I described, namely to combine the fitted values of beta with the measured values of the sigma 8 of the galaxies and put them together. When you do that, you get a value of this parameter f sigma 8 of 0.401 plus or minus 0.017. So that's about a 4% uncertainty. And that's for the data that I just showed you from a paper by Barua et al. So supernovae and Tully-Fisher. Now we've also done the exercise with a data set of fundamental plane measurements that was compiled by Khaled Said from the 60F survey and the Sloan survey put together. And those give you a slightly lower number, but with larger error bars. Okay, so if you combine both of those, you get an F sigma 8 of 0.383 with formally very small uncertainties. So we can convert those F sigma 8s into this value of S8 that we've already heard about. And here's an updated plot from the one that appeared in Barua et al. It's updated only to include the ACT DR4 plus W map results on S8 that we just heard about from Colin Hill. So these are grouped by method. So we've got the CMB on the left, and it shows that ACT, DR4, and W map also have a high value of S8, consistent with Planck. And then we've got some other methods, cluster abundances, which I won't say much about. Weak lensing, which we've heard a lot about from Marika, amongst other people. We unfortunately didn't get the DES Y3 results that I was hoping for, but nevertheless, that will be an important survey. And you can see there were hints of the S8 tension even in the older survey labeled CFHT, which is the CFHT lens survey that was led by Catherine Heymans and Ludo van Verbeek, and I was involved in that as well. That didn't cause so much media attention at the time, because at the time the dominant S8 value was from WMAP, which was lower. And of course the error bars are quite a bit larger than they are today. Finally, we've got peculiar velocities measured 2 different ways on the right-hand side. Redshift space distortions is what many people are familiar with. They also give you a value of F sigma 8, which you can easily turn into S8. But redshift space distortions, as I mentioned, are dominated by cosmic variance, and so their uncertainties are very large. So here's a compilation of work from the eBOS team, which also includes the older BOS data. And finally, we have direct measurements of peculiar velocities of the type that I've described, And the 2 points that I just mentioned are the two on the furthest right, Barua and Said et al. And so if you are just naive, and you shouldn't really do this, but if you want to get an idea, you could put all these data together, slightly disregarding the fact that they're not all independent of each other. But to a first order, they are sort of independent. And you would get this value of S8 of 0.76, plus or minus fairly small error bars. It happens to land right on the kids' value, which is not surprising because the small uncertainties of the kids do pull it. But you can see if you look closely at the error bars that peculiar velocities have the potential as well to give you very tight error bars. In particular, compared to redshift space distortions, here's the same plot again, but it's meant to highlight the fact that when you measure redshift space distortions, there are about 2.3 million redshifts which went into this estimate here. Whereas for peculiar velocities, we're talking about maybe 20,000 peculiar velocities. And with that, in principle, you get smaller uncertainties. So it's a powerful probe for measuring S8. Of course, the BOSS measurements also measure BAOs, which are important. Okay, let me say a little bit about the dipole. The dipole is, I'm almost taking a step back here and asking the question, suppose now we focus on the velocity of the local group. So the velocity at r equals 0. I don't think you can see my pointer here probably, so I have to describe it. The integral that's written sideways on the left goes out to r max. So you can imagine changing that r max, and that's what's shown on the right, on the x-axis. And just focus on the purple, solid purple curve. So when we're talking about the predicted local group motion measured from 2m++, the CMB value is shown in cyan, and that's 600 kilometers per second and change. And what this curve shows you is that when we put in the best fit value of beta, we recover nearly all of that motion from this 200 kilometers per second. You can see it falls just a little bit short. Okay, so already we've explained most of the motion of the local group. It's not a great mystery in this picture. We understand in particular that the rise of it that goes out to coming from structures within 50 megaparsecs, okay, is what we call the great attractor. So there it is. It accounts for more than 2/3 of our motion, the structures within 50. But then there's a slow sort of logarithmic rise as you go out to larger scales. The alignment, by the way, in direction is excellent. So the purple curve, the alignment is not shown here, but it's within 10 degrees of the dipole. So that brings us to the other term, this V external. That's to make up for all the stuff beyond there. And when you fit that as a free parameter, it comes out to be about 170 kilometers per second. So in other words, we can take our model of the velocity field and use that to predict what the bulk flow should be in spheres of different radii. In fact, these are Gaussian shaped spheres. And the predictions shown in blue, okay, and the data are shown as the points, including the 6DF data, as measured by Morag Scrimgeour in her careful paper, which is plotted at a different distance from what Subir showed yesterday, which is from a conference proceedings. So I think this is the correct value for the 6DF, and it shows that we're not in conflict with that. So in a nutshell, 2m++ motion accounts for most of the motion of the local group. If we compare different peculiar velocity surveys, okay, each one gives a measurement of this external contribution, and it's always in the range of about 160, 170, 180. Whether we measure it with supernova and Tully-Fisher, whether we measure it with 60F fundamental plane, or whether we measure it with SDSS fundamental plane. The amplitude and the direction are very consistent and are consistent with other analyses from different groups. So there is still some missing contribution to the local group's motion that we haven't mapped perfectly. It should be either beyond the limits of our survey, which is 200 megaparsecs, or possibly in regions of the zone of avoidance where we also don't have good data. So there's still work to do, but we're not talking about thousands of kilometers per second that are unexplained. We're talking about only of order of hundreds, less than 200 at most. So I think the puzzle of the local group's motion is 75% solved. All right, before I wrap up, I want to show you one other application of having a peculiar velocity field. We've used it to measure the cosmological parameters, but it also has impact on the Hubble diagram. Okay, in other words, we can predict the peculiar velocity everywhere with our model, having fixed these two free parameters. Here's an example in the context of gravitational wave sirens. So as you know, we measure a Hubble parameter if we divide the redshift by the distance, but what we really want is the redshift in the free of peculiar velocities. Okay, in other words, this Hubble redshift is the measured redshift minus the peculiar velocity. Okay, and so to get this peculiar velocity, we just use our density field and integrate it up, and we fix those two free parameters. So you can do that for the gravitational wave. It's not very exciting on its own because its uncertainties in H0 from one gravitational wave with an EM counterpart are fairly large. More interesting is if you apply the same method to megamasers. Okay, and with megamasers, we can apply that to each maser point by point. And we get, when we do that, the full integration, this is in another paper by Supranta Barua, we do find a slightly lower value of H0 than they found in their paper where they did the peculiar velocity corrections in a different way. I should say that this has been submitted but hasn't finally been accepted, and I think that probably our best value today after discussions with Don Pesch and Mark Reed, as well as Adam Rees and Supranta, is probably 70 kilometers per second, because the uniform distance prior may be actually the better estimate to put in. Somebody wants to ask me in the questions, I can explain in a little bit more detail. So it's a little bit lower than what they found, and right in between the the Planck values and the Shoes values at the moment. So if you want to play with this yourselves, you're welcome to. You could just go to the website at the bottom, cosmicflows.iap.fr, and you can generate your own predictions as a function of distance or for specific galaxies. Okay, so I should probably wrap up. I think I'm a little bit over time, but I did have some technical issues, which hopefully the chair is giving me a bit of grace for that.
No, you're fine, Mike. You're actually right on time, even with technical difficulties.
Okay. So the take-home messages are that for measuring F sigma 8, you get highly competitive constraints on it from only 20,000 peculiar velocities using linear perturbation theory. And as you can see, these values are in agreement with the ones from weak lensing in particular, but of course are in tension with this Planck normalized lambda CDM model. And the second more minor point I think is that this volume that we've covered explains almost all of the local group's motion, about 3/4 of it, leaving about 170 kilometers still to understand. And I'll stop there. Thank you.
Thank you, Mike. Thank you. We heard you much better since we switched to Plan B with the slides. I'm really glad that worked out. So we have some.
Okay. Should I turn on my camera again?
You can. And we'll shut that down if there are problems again.
Okay.
So first, we had a very quick question in the chat. Are these velocities with respect to CMB coordinate from Mohammed Ansari Fard?
Yes, everything I quoted was in the CMB frame.
Okay, right. That came up yesterday also. Then we have a question from Adam.
Hi, Mike. Can you hear me?
Yes, I can.
Okay, very nice talk. I especially like the second half where I could hear things more clearly. My question is, so an underappreciated aspect of the distance ladder measurements with type 1a supernovae is the application of the peculiar velocity corrections. When we apply them, it raises the Hubble constant by about 1%. And in fact, this is a difference between the analysis for shoes. We apply the 2m++ corrections and it raises H naught by 1%. The CCHP analysis does not apply the peculiar velocity corrections. And I guess my question, and that explains about 1% that explains a good chunk of the difference, about 25% of the difference. My question for you is, should we be applying these peculiar velocity corrections? And if we don't, are we trading, like, I could not apply them and I can get lower tension with the CMB, but am I trading tensions? Am I creating a tension for you because am I setting beta equal to 0 and the external velocity equal to 0 if I don't apply them?
Well, my view, I was trying to argue, is that, you know, this is a correction that you should obviously take into account. You may choose somebody else's models, but, you know, for measuring the Hubble parameter, we need to have the velocities free of these peculiar velocities. It would be like saying I wanted to do photometry, but I'm going to choose to ignore, you know, galactic extinction corrections. So that's sort of the way I see it. Now, you know, there's obviously issues of how you apply it in practice. I should take the opportunity to say that what makes the most sense and what a lot of people don't do, and is a source of some confusion, is that if an object is in a group, you want to first correct to the mean redshift of the group first, and then you want to predict the peculiar velocity of that group. It doesn't make any sense to leave in these sort of extra random small scale motions. I'm not sure that really answered your question since I went on a slight tangent, but hopefully it's helpful.
Sure. Thank you.
Colin. Colin, you're muted. Yeah, you're okay.
Yeah, sorry, I lost the mic. Can you hear me now?
Yes.
Yes.
Okay, great. Yeah, thanks for this great talk. I had two questions. So one was back when you were talking about the n-body or the simulation tests of the assumption of linear theory here. Exactly how was that done? Did you populate the n-body simulations with galaxies in some sort of way, or was it just done with the halo catalogs from the n-body simulations?
So good question. We actually did it with both. Well, we did it with the particles as well, and we did a successive stage, checking the particles, the halos, and then we used the, so this is from the, you know, a Bolshoi family MDPL2 simulations, which have two different semi-analytic models pasted onto them. One is called SAGE, and the other is called, confusingly, SAG, by two different groups. And so we just use those catalogs downloaded from that source.
I see. Okay. My other question was about, this is actually, you know, kind of just looking at the future maybe. Have you thought about whether it would be possible to combine your very local peculiar velocity catalog with CMB data to make some interesting KSZ-based measurements of the gas profiles associated with these objects? For the galaxy formation crowd, this is the kind of thing that they love. So this might be interesting to try.
Yeah, as you know, your collaborators and you yourself, I'm assuming in ACT, have done this using a different velocity fields at slightly higher redshifts.
Yeah.
Niesh and I had a go with Guillaume Lavaux. Lavaux was the lead author of doing this way back, and using these models as a template to predict forward in the same way that you guys do. The problem there was we did it with WMAP, and it was only sort of a marginal detection of the signal at all, let alone the profile. But now we have better data. We could revisit the issue and see better CMB data. I mean, the predictions haven't changed as much. The disadvantage, I guess, is probably that the volume may not be as large as other volumes, like the Boss volume, for example. Projected onto the CMB, it's only a small chunk of the momentum field. We go out to 200 H inverse megaparsec, so that's Z of 0.067.
The main reason I think it might be interesting is just that they're so nearby that you could actually start to resolve the inner regions of the halos, whereas that's generally a challenge for us at the higher redshifts.
That's a good point. Maybe we should talk offline.
Yeah, I think it'd be interesting. Thanks.
Because with your higher resolution ACT data, it's going to get better and better, right?
Yeah, I don't know if the statistics will work out here, but it's definitely something we should estimate and see if it might be possible.
Okay, thank you. Roya. Microphone. Thanks.
Hi, yes. Thanks, Dragan. Thanks, Mike. It's good to see you at distance. Really enjoyed your talk as always. Thanks very much. I just have a question. As you can imagine, I have zillions of questions to discuss with you, but let me just ask one. I'm going to ask a question about this dipole. And I think your results agrees actually with what we did with the supernovae and also with 2MRS, as you know. But I wonder whether it agrees with what you did yourself with Hume-Feldman and Watkin some years ago. And I think there you had a real discrepancy. And I'm just wondering what's happening. Can you just elaborate on that, please?
Let me address that. It's in this plot. If I go back a bit. So the point you're talking about, I think, is shown in this diagram labeled WFH. Now that point is high. It is still high compared to both our model and compared to sort of lambda CDM, which is shown in the green. And my own personal view is that this is what it looks like, a 2 sigma fluctuation. In other words, we've subsequent to this, of the data that are plotted here, that was the first one. And then the THF was a supernova result led by my student Turnbull. And that on the same scale got a lower value. And then we have other measurements like the 2MTF and the 6DF. All of those 3 later sets seem to be consistent with our model. The WFH, Watkins et al. Is still high, but probably not much higher than 2 sigma, I would guess. We could go back and revisit it more carefully.
Okay, thank you. Konstantinos. Microphone. Now, yes.
Okay, good. Hi, Mike. It's Kostas from Bonn.
Kostas.
I'd like to ask you, what kind of a mass concentration would you need to explain the residual bulk flow beyond 0.07 redshift or so?
Yeah, so remember that, again, we live in a Gaussian random field, so it's probably not one individual mass concentration. Now, if you look at what lambda CDM predicts on those scales, lambda CDM says, okay, it's a bit tricky, right? Because we don't have a nice clean sphere that ends precisely at 200. We have this funny volume that goes out to 200 in most of the sky, is a little bit shallower, and is also missing some area in the galactic plane. But let's imagine, for the sake of argument, that it does go exactly out to 200. If that were the case, then you can use lambda CDM to predict what the contribution should be from beyond that radius. And it is about 40 to 50 is my recollection in each direction, in each of the 3 Cartesian directions. So if that, at that comparison, there would be a little bit of tension with normal lambda CDM fluctuations. But then there's these caveats that I said that the volume is actually smaller than that, and in particular is missing stuff in the plane. So at this moment, I don't think there's any compelling evidence that normal LCDM fluctuations cannot generate that extra amount. What we're doing right now, this work in progress, we don't have any answers to this question, is trying to build full simulations of the 2m++ field from these MDPL2 to better assess the statistics of that quantity as well as other quantities, other cosmological quantities.
Okay, thank you very much.
Thank you.
And a comment in the chat by Subir Sarkar saying 6DF result I showed in my talk was a different one from Skrimegor et al. It's a much larger distance. It was shown in the IAU Zeldovich conference, which I think agrees with Mike with what you said.
Yeah, so I actually looked at that because I was very puzzled by it. I actually dug it up. I was even at that conference. And I have to say I don't understand it at all because it was plotted at, I think, judging by eye, 300 or 400 H inverse megaparsecs. So that's a redshift above 0.1. But the last data point in 6DF ends at 0.05. So to me, the Scrimgeour, knowing what I know about the 6DF redshift distribution, the one that's plotted in the IAU doesn't make any sense because the data don't actually go out that far.
Yeah, that sounds like a bit of a puzzle.
My suspicion is it was just a plotting error, but you would have thought since, I don't know, I don't want to speculate.
Well, I believe that's all of the questions, and coincidentally, we are basically right on time. Thank you, Mike. Thank you, Colin. Thank you, all the speakers today and the parallel session. It was a really good, really exciting day of talks. We will meet again tomorrow. Let me see if the organizers have anything to say at this point.
Okay, thank you, everyone. Thank you, Dragan. And yes, okay, for tomorrow, we will have a little bit of change in the schedule, maybe. I guess Galen Starkman talk will be a little bit earlier. So, and it's it for today. Thank you very much, and see you tomorrow.
Thank you. Goodbye, everybody.
Thank you, Mike. Thank you very much. And Galen, if you are here, please raise your hand. Yes, here. You can, yeah. Galen, can you hear me? You should see a microphone on top right. Glenn, if you hear us, maybe you can write in the chat box if you cannot hear us.